Test 1, 2, 3, test 1, 2, 3, test 1, 2, 3.
I'm using both. Test. Test. Okay. Let's just wait 4 more minutes, or we're still waiting, right?
Oh, we're still waiting?
I mean, I would still expect. You don't think it's gonna be more than this? Like 9:25?
Oh, nothing. Okay, so good morning, everyone. I hope you had managed to get some sleep last night, and I hope you enjoyed the gala dinner. We didn't get to announce the Best Poster Awards, but they're coming. We will announce them tomorrow morning. And today we'll slowly get started. So maybe very first thing, I'd like us to give a big round of applause to Marco, our streaming person here.
Thank you so much.
And now we'll get started. We have Suad Klasevic, the representative from ANT, who was our hosting organizer last year in Bosnia and Herzegovina. And we're still very grateful for all the effort that they put last year in organizing a fantastic EML edition. And we're very happy that we're really managing to bring together the Eastern European community, like bringing together the partners that we had in previous editions, and of course, Ant helped us a lot actually this year as well. And we also have AI Albania that will be with us tomorrow morning, actually presenting, and Arya from Romania. So we have multiple NGOs now involved in the summer school, and we are really happy to have this community coming up. Okay, so Suad, up to you. Thanks.
Thank you all for coming. So this morning I have a very difficult problem. I have to present my organization to a bunch of sleepy students. So let's say I will try to make this presentation a bit interesting. So let's say your attention is a function of sleep, coffee, and relevance. Relevance. Forgive me if I misspell something. Plus one. I cannot affect these two. So I'll try to make this presentation a bit more relevant than just an NGO in Bosnia. I'll try to prove mathematically that volunteering is optimal behavior. And INNT, my organization, as an example. Okay. Are we good? First part of the proof. Gradient descent. Gradient. So I think all of you have studied gradient descent. Let's say this is your loss function. And we are starting here, like 0. So what is the problem with gradient descent usually? Let's say specifically in this function, what will happen? Local minimum, exactly. So if we were using gradient descent, xk plus 1 minus gamma delta L over xk, we would be taking steps slowly, smaller, 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 until we reach the local minimum here. Of course, if this gamma is properly set and whatever. We won't go into strict mathematical details on this lecture. Why does this happen? Zero gradient, yes. But why can't gradient descent reach the global, let's say, minimum? Philosophically. Sorry? No. Greedy choices, exactly. So gradient descent, they call it a greedy algorithm. Why greedy? Because it chooses the action that is locally the best one. So locally best. So from this point, it looks like this is the best direction to go in general. But as you see, the problem with the greedy approach is that it doesn't have the bigger picture in mind. So if you just follow the gradient descent, you will get stuck here, but because in this point, the gradient is zero. But since you're only using the greedy strategy, you're only looking locally, you don't see that there's a better optimum somewhere here. So to reach a better solution, we have to use non-greedy strategies. Let me highlight. So this is the first part of the intuition. Second part. Does anybody of you know what is a Nash equilibrium? Equilibrium. I think it's spelled like this. Does anybody know what's a Nash equilibrium? So we have like 5 to 10 people. Okay. So to explain a Nash equilibrium, it's best to use an example. But before I give the example, so optimization is when you have one cost function and you have complete control of this cost function. You have control of all the variables. So this is the usual, let's say, case in, let's say, data science. So yeah, you know your loss function. I say cost, but yeah, you say loss function. Loss function, you know your state, you know your variable, and you can optimize this however you want. In the case of the Nash equilibrium, you have multiple cost functions. So you have L1, L2, blah, blah, blah. We'll stick with two cost functions. And your cost function depends on your actions, but also on somebody else's actions. So you depend on others somehow. So you have no control over this. You depend on others. So the usual example is how people explain the Nash equilibrium is with the prisoner's dilemma, but I'll choose something maybe more familiar to you. Let's say you have a roommate. And somebody has to do the dishes. So dirty dishes. And you're playing with your roommate the game, who's going to do the dishes? So let's say this is you. This is your roommate. Or better, right here, roommate. You have two options: wash. No, not wash. Same. Your roommate has the same options. So let's say both you and your roommate choose to wash the dishes. It will take you 30 minutes to do it. If you decide to wash the dishes, but your roommate decides not to help you, it will take you 30 minutes. If you decide to wash the dishes, to not wash the dishes, and your roommate washes the dishes, it will take you 0 minutes. So this is the, the best scenario. And let's say neither of you chooses to wash the dishes. Then you just have a big pile of dishes the whole week. Like every time you have to cook something, you have to take a part of the dishes from the big pile. You have to make room on the cupboard. So it's always a mess. So it takes you more time to cook. So it takes you in for the whole week, let's say 40 minutes. So let's see if you were behaving like optimally, what would be your best strategy? Slowly. So let's say you know that your roommate is going to wash the dishes. So we are looking at this case here. What is the best option for you? Not to wash, exactly. So if you know that your roommate is going to wash the dishes, for you it's best to not wash the dishes. So this option here. In the other scenario, if you know that your roommate is not going to wash the dishes, what is the best action for you? Also, not to wash the dishes, because if you wash them, it will take you 60 minutes. If you don't wash them, it will take you 30 minutes. You see this logic? And so whatever your roommate chooses, for you, it's the best option to not wash the dishes. Your roommate has the same table, let's say, in his room, if he's doing calculations. So for him, it's the same. So for him, it's optimal not to wash the dishes. So if you're not washing the dishes, if he's not washing the dishes, you both end up in the option that nobody washes the dishes. Okay? Is this clear? So this is what's called a Nash equilibrium. But in essence, you see, this is, let's say, the worst case scenario, like the scenario in which the most time is wasted. Like in the first case, if both of you choose to wash the dishes, it will take you 60 minutes. While in this case, it will take, so each of you 40 minutes, it will take 80 minutes in total. So if you are like some sort of global optimizing time function, or doesn't matter, this is the worst case scenario. But this is the scenario that if you're just optimizing greedily, selfishly, let's say, you end up with in. So a Nash equilibrium. Equilibrium. is a point from which no agent can leave following his selfish strategy alone. Alone. So if you're an economist, you would say, okay, this is how I want my society to be structured using a Nash equilibrium. So everybody is a selfish agent, everybody is maximizing their cost. And yeah, this is the scenario. But if you're a normal person, you would say, okay, if we want to get the best scenario, if we want, let's say case, we have to cooperate. Okay. And the last part of the proof. I think most of you have seen this meme. So it's time, energy, money. So, and they say when you're young, you have the time and the energy, but not the money. Bless you. Somebody was sneezing. When you're a bit older, you have the energy and the money, but not the time. And when you go into retirement, you have the time and money, but not the energy. So we can say that wait. Hmm. Comfort is our cost function of an individual, and it's equal to time plus money plus energy. But is there something missing from this? So this is not, this is not everything that matters in life. You get comfort also from the, let's say, from the community. So plus community, I think this is not spelled like this. So if we go back, if you remember what we were saying about the Nash equilibrium, your cost function doesn't depend only on you. So this is your contribution. This depends on you. This depends on others. And this function, as you can imagine, is very nonlinear and it goes in all directions. And you can imagine it looks something like this. So people are usually minimizing their negative comfort, let's say. And to me, using time, money, and energy, so you're using this is volunteering. Using. So in order to get, let's say, the bigger community contribution and to increase your comfort, you need to sacrifice time. You need to sacrifice time, money, and energy via volunteering to get the bigger community contribution. So you can be able to leave this local minimum of your, let's say, comfortable life and get a better solution somewhere here. Of course, it depends what your community is, what your surrounding is. In some countries, it looks like this. In some countries, it looks maybe like this. So it would take a lot of effort to go over this. You would need quantum tunneling, maybe. So I've shown that in order to reach the global optimum of your life, you need to spend your time, energy, and money to reach the better solution. QED. Okay. Now I can give you a specific example of my organization. And let me switch. X. Shit. Your screen sharing? Everything good? So I will give you a brief overview of what my organization has been doing in the past 9 years. Or soon. Oh. So the English translation of my, the full name is Asociacija za napredak nauke i tehnologije, but the English translation is Association for Advancement of Science and Technology. We were founded in 2017 by a bunch of, let's say, young scientists that were scattered around the world. Some of them were in Bosnia, some of them were in Austria, some of them were in Switzerland, some of them were in England. And we wanted to do something good in our country. So, like I said, we started in 2017. I think in the beginning we had like around 10 to 20 members. I don't remember exactly. Zlatan is also from the association, and we've been we've been together since the beginning, like since the founding. And now, today in 2016, we have around 150 members, out of which I think a bit more than 40 are PhDs, so have a PhD. And we have completed numerous projects. So this is the project we've been doing for the longest, let's say. We started doing this from 2018. The goal of this project is to bring young high school students in one place from whole Bosnia, and to show them interesting lectures from successful Bosnian researchers from all over the world, and give them some practical tutorials, some practical things to do, and also to connect these children. Like I've been attending most of these events since the beginning, and it's really fascinating to see these children, like to interact with them. Usually we book a student dormitory for a few days, and like they play games until very late, a lot of them really get some useful insight. Like it has happened several times. They say, "Oh, I wanted to study this, but when I saw this lecture, I realized this is not for me. Like I will do something else." So we helped a lot of students, let's say, find what really interests them. Mm. So the previous level was high school level. this project is more bachelor master level. The idea of this project is to connect our members, researchers, with students that want to work on some interesting projects. So our members create interesting research problems, and we make a public call so any student from Bosnia can apply to it. And for around 6 months, we do a small research project. And for many of the students, this is the first interaction with science, like the first time they had the opportunity to do some serious science. And a lot of we already had a few examples where the students told us like this project is what helped us get a position on some or maybe a PhD or a master position at some Western university. So this has been a very impactful project. So this is the project where I was also very much involved in. Bosnia and Herzegovina has one of the largest diaspora in the world. I think that the statistic is 50% of all Bosnians live outside of Bosnia. So it's a very high. And we created a platform to try to find all of these researchers. There have been some attempts to find these researchers to connect them, but they're all they fizzle out in a few years, or they are based on voluntary, let's say, people saying, okay, I live there, I'm connected to Bosnia. This attempt was more, let's say, of data mining. Like you have papers, you find the names of the people, you see what's the name of the institution. So this way we managed to find, this is an old picture, but we managed to find around wait a second. So this, the number there, 3,400, this is the number of researchers somehow connected to Bosnia we managed to find. And we have over the 45,000 papers on this platform. Besides this, we were trying to do some, how to say, not just help the students and high school students, but also to do some meaningful change in the country. So we were helping by writing some strategic documents, let's say. So this is a paper that Zlatan here, he was the, let's say, the lead author, and we wrote this in 2021, I think, 22. So this is one of the papers, but we wrote several of them. There was another one. I was also involved in writing like some strategic documents for application of digitalization and AI in Bosnia, but we will see what will happen with that. So we are also working in this dimension, let's say. And last year, wait me. So we also helped organize last year's EEML. In Sarajevo, we had over 300 participants, 900 applications, so a bit less than this year. A bit. But it was a very fun event, and we managed to again help a lot of, I mean, not only the international, let's say, the Eastern European community, but also the Bosnian community, because I think we had most of the participants were from Bosnia, and for most of them, this was the first and only chance they ever had to experience an event like this. And I just want to say, in the end, maybe, of course, you're participants, but you don't realize how much time and effort it takes to organize an event like this. Like usually the meetings start from January, and you have a meeting every week. That's just the meeting. That's like half an hour. Then you do your tasks. Like in 6 months, this accumulates a lot of time. And imagine if you decided, okay, I want to spend an hour every week to help with something. Like how much effect this would have. So, yeah. I mean, the organizers will get an applause tomorrow. But just to emphasize the point, to really have a broader change, I think you really need to reach out, see if there's somebody in your community that's doing something. Say, okay, how can I help you? Like, don't just selfishly maximize, okay, money, time. Like, you really need to help out. That will be all.
Okay. Thank you very much. Okay, now I think we have the mathematical proof that you do need to get involved in your communities and help them grow and give back to your communities. So thank you very much, Suad, for that. Okay, I think just a couple of announcements. I shared this morning the slide deck where you can add pitches for your projects. So tomorrow you'll be presenting your pitches. Please add slides to that deck. If you have any questions, please reach out. So this morning we were scheduled to have Nicholas Hess as a lecturer, but unfortunately he couldn't join us very last minute. He's really not feeling well. He couldn't travel. But he has really exciting robotics work that he wanted to share, kind of in premiere actually, because it launched, I think, last night, and he was planning to share this morning here. But yeah, unfortunately he couldn't travel. But we have very nice alternative for you. We will actually hear about AI for medicine with Elma Dervic, who is a research fellow at the University of Vienna. And Elma is actually also part of the organization team. So we're really happy to have Elma, who is actually an alumni of University of Montenegro, and she did her PhD in Vienna. In general, she's interested in machine learning and network science, and more generally, AI for social good. So let's give a big round of applause for Elma, and thank you very much for stepping in.
Thank you all for coming after a nice gala dinner. We'll need a few minutes to prepare a setup. Thank you, Verica, for the introduction. I will try to keep this lecture light and about my research project I did during my PhD, but I'm aware you're all sleepy, so we'll keep it short. Alinea. Yeah, full screen. No, continue. Neće. Ali neće prezent. Neće prezent. Neće. Ne vidi se uopšte u full screen. Nemoj da šaruješ, znam šta je. Šaruj cijeli screen, nemoj samo Safari. To je problem. Sad se sjeti. Ne, to je sve. No, pa ne. Ali nema sve lako ću. Sporo je kao to. Okay, technology is not on our side, so let's do it like this. Looking at the data from last century, we see that we live longer than our grandparents. Longer life, however, doesn't mean we will be living our 20s and 30s 2 times. Longer life means 80s, 90s. Longer life means multi-morbidity. Aging means we need additional support. Looking at the statistics from EU, we see that our seniors are already quite sick. Unfortunately, 30% of them require long-term care. Now, when I hopefully convince you that we are aging population, we are in a huge problem. Now, hopefully, we will understand why I was so passionate about my research project during my PhD. I was lucky enough to do my PhD at a medical university in Vienna. And what I was trying to do as an electrical engineer with a little bit of medical knowledge, I was trying to understand how patients aging, how they're collecting diseases, while some 80 years seniors are healthy and fit, while others are spending days in hospitals. In order to do so, I got some help from Austrian Ministry of Health, and we got access to this amazing data set. Hopefully, many of you would like to work with some kind of data set, which is a real-life data set, on the whole Austrian population. So basically, if you're from Austria, you're already part of our research. If you skied in Austria during 1997 to 2014, you broke a leg there, you're also part of this research. So thanks to the Ministry of Health, we got access to the medical claims data. What is really cool about this data source is that no one invested time in collecting it. This data source is already there. It's collected for insurances. So what you see here is secondary use of this data source, what we have in the data source. So basically we have all hospital admissions, 45 million hospital admissions on basically all Austrians, 9 million individuals. We can see when someone visited a hospital, how long they stayed, in which department of hospital they stayed. We see the main reason for hospitalization, which you will see a lot in all my slides, ICD-10 codes. That's a standardized way of coding diseases. We also see how old is patient, we see from which region they're coming, obviously we see their sex, we see if they died in a hospital. So it's quite rich data source. We also have another data source where we got information also on nationality. You may predict, but Austria is welcoming a quite huge number of international researchers, students, workers. So in a collaboration with ministry, we also get information on nationality, which is then allowing us to understand which difficulties have Balkan people in Austria in getting healthcare, which difficulties maybe have Turks. Are there some issues which are then causing their health to deteriorate? At the end of the day, how much that costs ministry in Austria. So besides some simple statistic project I was developing in a collaboration with medical doctors, I mainly focus on understanding this strange name, cradle to grave disease trajectories. What came as a surprise to me as an engineer was that the whole healthcare system is built for males. In females, well, we have to fit in the system built for males. Luckily, using AI and data science in these kind of data sources, now we can also address this kind of issue. We can look at the females pattern, males pattern, and we can help make the healthcare system more fair. So before jumping into some of the results, let me introduce you one concept. I'm part of the Complexity Science Hub, and we are in love with networks or graphs. We believe that one of the best representation of the world can be in networks. In order to understand diseases, we don't want to look at the diseases in isolation. Probably it happened to you, or maybe it didn't, but maybe for your parents or grandparents, it happened to you that you go to the doctor to, I don't know, treat diabetes, and then you go to another doctor to treat obesity. From our point of view, that doesn't make sense. We should look at the whole system. We should look at all diseases at the same time. In order to do so, in order to represent diseases and our data to have some math in the background, we introduce concept of comorbidity comorbidity networks, or actually we are using introduced concept of comorbidity networks. So if we want to understand all diseases at once, what do? We look in our data. I won't go into technical and statistical details, but in a nutshell, we want to understand, is obesity somehow correlated with depression? We look at our data, do some boring statistics in a background, and if that's the case, we put a link between obesity and depression. I mentioned ICD-10 codes. Obesity in ICD-10 codes is E66, and depression is F32. Hopefully you don't know that. In our networks, it will look like this. One important note, I'm not talking about causation, and using our data, we can't really say that one is causing another. We just see in our data that our patients have more often these two diseases together than what you would expect at random. So that's why we don't have direction. We don't know direction. So we put both directions on these two diseases. If I repeat this exercise, I will get something like this. I know it's a bit complex plot. So each bubble is a disease. Color corresponds to disease type. For instance, here you see orange bubbles. These are cardiovascular diseases. Also, in different parts of the networks, you see different types of chapters or disease types. And here you see one of the big nodes, which is quite relevant, that's hypertension. For basically, hypertension is one of the most relevant diseases in females in 40s. And as I already told you, link is encoding a correlation. We have some bigger links between diseases, and I can tell you that in this region, we have cancers. Maybe you can guess what is the biggest bubble here in females in 40s, what that could be. Exactly, it's C50, it's breast cancer. Okay, so different regions encode different types of diseases, and now maybe I can go further and show you how these networks evolving over time. So we have kids, teenagers, adults, and then seniors. And then what is expected, obviously, when you're younger, these networks are not so complex. However, things start to become more and more interesting, at least for our research, when you become older. So what you see in this animation is basically 20 years of data on 9 million individuals encoded in these 8 layers of network. Okay, so I'm aware that not all countries are allowing researchers to have access to this kind of the data source. So what we did, we decided to share it as a data resource. Maybe for some of you will be interesting for a master thesis or PhD thesis. Basically, all of these networks I show you, we shared as a data resource in scientific data journal. And you can assess it, you can analyze it. And believe me, even though this data is quite aggregated and there are no patient level data, still we can learn a lot just by using these networks. For instance, here we are interested in some network properties, like how topology of these networks is changing over time. Also, we are interested in like a comparison between females and males. Interestingly, at this scale, we can then understand which are the most central diseases in 20s and 30s, how these things change. I mentioned sometimes we see a patient died in hospital, which means we can associate disease code with mortality, and then we can see which are the most central diseases, in which time of life of patient, how they're connected to other diseases, hopefully with idea to learn more, to identify some patterns, which will help us later to do better prevention. Well, maybe you will ask yourself, well, this is Austria. Maybe it's very biased. Maybe it's just like Austrian thing. Maybe you organize healthcare system and patterns you see are only Austrians. This is very valid concern. And what I'm trying now with colleagues around the globe, we're trying to look at these same data sources in different countries. From South Korea to the US, we have like more than 100 million patients, and we will try to validate what we learned in Austria worldwide. Well, at the beginning of this presentation, I promise aging, trajectories, pathways of patient. In order to do so, we use our networks across age groups as the layers in a multi-layer network. Up until now, I was always talking about correlation, but it's more interesting, it's more useful if we could somehow find some kind of causation. At this point, I already have many medical doctors who are angry looking at me and saying that these things are more complex and it's not so easy to understand causation. So what we did, as we have 20 years of data, we track our patients and we track patients who came to the hospital in 20s and they also return in their 30s, which allow us to look at obesity in 20s and depression in 30s. And we checked if cohort of patients who were obese 10 years earlier, if they have elevated risk for depression later in life in 30s. If that's the case, now I'm allowed to put a link between these two diseases, but this time I have direction. I have some kind of temporal aspect because my patient aged during these 20 years, and I can say that having obesity in 20s is elevating your risk for depression later in your 30s. Okay, so I will skip these nice applications and jump into the super simple model, which is unsupervised community detection algorithm, which is coming from the network science community. Like many years ago, it's published, where we optimizing a super simple fitness function in order to find clusters on this quite huge network. So what we do, we start with a random node in the network, and then we are just like expanding this community, adding more nodes to it, checking the fitness function, repeating this until we converge, and then we close our community, continue with the next nodes, and eventually we, at the end of this process, identified communities on our huge network. So thanks to my colleagues, I have this nice art piece rather than a graph. So we did this on our huge network, which we built on the hospital claims data from Austria. And we identified 600 communities, 600 something communities for males and for females. So each of these gray regions are communities. Each dot inside is a disease. But I mentioned at the beginning, these communities are overlapping communities. Why we decided to use this method instead of some clustering method where we will find exclusive clusters? Well, in a communication with medical doctors, we learned that one disease can be very different in different patients. For instance, we have obese patients who are quite healthy. They don't have any cardiovascular diseases. They don't have metabolic disorders. Everything is fine. And on the other side, there is different type of obesity where someone is obese and had many other comorbidities. That's why we have overlapping communities, because we believe that one disease should be part of more communities and more pots. Okay, so if you're a patient, you would rather stay in this region where things are not so complex and you don't have elevated risk for many diseases. However, this is a danger zone, and it's interesting for our research. Like the most interesting results are coming from this danger zone. Okay, I can skip this. So in order to convince people that extracting knowledge from these kind of data source is possible, like even using some simple statistic, I prepared this plot to show that in our data, for each of the path, each of the trajectory we found, we can associate mortality, number of diagnoses, number of hospital days for each trajectory. So we can, for each trajectory, describe outcome, and we can show that some trajectories are more severe than others. I won't go into further details. I will just give you some simple examples, which everyone can understand, even if you're not a medical doctor, like I'm not. So looking at these paths, as they are overlapping and sharing diseases, we learned that these trajectories can overlap in different ways. And for us, the most interesting pairs were diverging trajectories. So basically, two patients are completely the same or quite similar in their 20s and 30s. Later in life, they start diverging, and one branch ends up in a cluster region, while others is just like something easy, not so severe. So that potentially maybe allowing us to say that using all of these exercises on medical claims data is allowing us to find critical events in a patient history. For instance, here we have one example chosen by medical doctors where we see that male patients with sleep disorder in their 20s and 30s are already on a path, on one of these three paths, and combination of sleep disorder in 20s and 30s is already a critical event, and maybe our healthcare system could be more proactive and can start doing prevention for diseases which might come later. At least that's what we see in our data. Are there some questions so far? Yeah. Okay, so yeah. So, oh, we can talk later. So basically, this is sleep disorder, this is sleep disorder. These are similar types of diseases from the same chapter. On another side, we have some metabolic disorder, lipid metabolism, obesity, diabetes. On another side, we have completely different, from medical point of view, pathway, but we can talk later. Any other question? Yes. I can't hear. Can you give it?
Thanks. I want to ask, which is the main difference between this kind of algorithms with the classical ones from data mining, like the association rules ones, and so which is
So why do we do all of this instead of just looking at the raw data?
yeah,
You-
they like the association rules, like the ones that you get like those buried and the probability that they are together and so on.
So the main issue here, why just pure statistics, something like what you would usually do first with looking at the data, the main issue that distribution of diseases is very skewed. So we have hypertension, which basically almost all of our patients have, and we have some super rare diseases. And then if we approach it without all of these exercises building the network, we will have a big issue that like these skew distributions, like comparing them, like something very different and like with many very different probabilities, comparing them. So we have to come up with some kind of solution, building all of these steps, building the network in order to have the whole diagnostic spectrum and to keep the full picture inside. Yeah, because many of the papers, you will see that they just filter like top most relevant diseases in order to learn things. Yeah. Hopefully this answers, yeah.
Okay, how do you create these single associations between like one condition such as like sleep disorder and the mentioned diseases as like maybe diabetes, hypertension, things like that? Because they have so many factors involved when it comes to diagnosing this type of diseases, such as like family history, lifestyle, and so many things. Like, how do you create these XY kind of relationships?
You're absolutely right. This is very, very confounded with many factors. We don't know it. So we literally just estimate what is the relative risk odds ratio between each pair of disease. And we are aware that it's very much confounded with all of these factors. Later in this presentation, I will touch some of these aspects. Okay, I can continue. So I talked a lot about disease trajectories, but I'm still locked in an Austrian ecosystem. I'm using data collected for insurance reasons. There are many biases in the data source. For instance, if hospital is not reimbursed for some diagnosis, this diagnosis won't be diagnosed as much as it should. For instance, obesity is quite underdiagnosed in Austria. Only if you're very obese, you will get a diagnosis. So knowing this, we know that we have many biases inside the data source, and then making some medical like conclusions is very hard. In order to validate that, we decided to use trajectories as a base, but we wanted to validate them and look at the biological mechanisms behind and understand if data collected in hospitals is really telling us the truth. In order to do so, thanks to my colleagues who are medical doctors, we decided to go on a molecular level. I didn't know, however, this field is like evolving, it's huge, there are many resources. And we identified these databases where we can find molecular profiles of all of the diseases which I'm interested in. So on the one side, ICD-10 code, on another side, molecular profile of disease. However, it's really messy. Like, I didn't know that it can be so messy. Databases are very different. They are covering different types of diseases. They have their biases too. One disease is covering more skin diseases than any other disease type, and so on. Besides that, one trivial problem, but it's still a problem, naming. In each of the database, one disease can have a different name. So breast cancer, in these databases, you will find under all of these names. So we had to get our hands dirty, do some data harmonization, and try to overlap these databases, all of them, to get one big harmonized database where we can say that we are covering majority of our ICD-10 codes. So you can see that some of these databases are quite big, some of them are smaller, and here is the overview of the harmonized disease atlas we made. And what we learned during this process is that, do you know what is PubMed? Yes, so like looking at these databases, we learned that actually more popular diseases on PubMed can also be more popular in the databases. So basically our attention is on this type of cancer. Suddenly there are many research projects, there's so many resources about this particular cancer. And then these databases suffer from this literature, we call it literature bias. So we look at the top reported diseases in PubMed and least reported diseases in PubMed. And then we realize that this like in ideal situation, this should be one, and then like one database is covering like nicely all type of diseases. In reality, that's not the case. However, when you harmonize and combine all of these data sources, we improve the literature bias situation. So at least in the harmonized data source where we have all of the databases, we cover nicely also rare and more popular diseases on PubMed. Okay, before going further, thanks to my amazing colleagues who are visualization experts, I can also show you some of the like apps we developed. Well, maybe to use this one. So when we develop something, for us, it's really important to communicate this, to make it accessible for medical doctors, interested public. So here you can see that if you have nicotine dependence as a disease coded as a diagnosis, there are many correlated diseases based on the medical claims data. And these diseases which are blinking, in our data, we learned that they're coming later. So they're kind of alarm. They might come later. So if you have nicotine dependence diagnosed, maybe later in life, you will get respiratory failure. Back to your question, in order to understand, is this biologically explainable or it's just a lifestyle? We took all of our results from trajectories and compare it to the molecular profiles on the PPI networks. Every link which has a number, like a bold, like a percentage, is showing a connection we could verify on a molecular profile. So these two diseases are connected in our hospital data, and they do make sense on a molecular profile. All other diseases, which we couldn't validate on a molecular level, they might be like due to lifestyle, they might be due to many other reasons, we don't know. Back to presentation. So for all those who had this scary, strict question, is it just Austrian thing? Is it that your data is biased so much that you're not learning something medically, biologically relevant? Well, data shows that our trajectories on a molecular level do make sense. Signals we found on the medical claims data is also on a molecular profile. So I will try to hurry up a bit. But I talked before that some trajectories have critical events. Some trajectories are more severe. And in order to check that on a molecular profile, we introduce stages. So every time when a patient is aging and getting a new disease, we introduce a new stage. And then having more stage means you're becoming more severely ill. What we learned looking at the molecular profiles of diseases, that this is also translated on a molecular level. So we saw that if you have like more severe disease progression, you will have more hubs on the PPI network. Your disease you have is more central there, which is confirming that these stages, actually the fourth stage, the last stage, is the most severe, even if you look at the molecular level. So maybe you are asking, why do we do all of this? Why this is needed? Okay, maybe to validate the previous project. Well, we believe we could do more, like looking at the trajectory like this, which starts as a small issue with your liver and ends up as a liver cancer or liver failure. Knowing this trajectory, knowing what's happening on a molecular level, maybe we could do some intervention. Maybe we could understand this progress better. And if you look at the PPI network, it will look like this. So not so severe diagnose looks like this. And later, with the progress of disease, you end up at this stage where it's all over the network and it's quite a severe issue, liver failure. So what we propose in the project is that knowing all of this about this particular trajectory, maybe we could introduce some kind of medication, some kind of drugs, which could potentially stop the process or slow down the process. In order to do so, we use this data source. It's called Drug Bank. It's a really nice data source from FDA-approved drugs. We look at all drugs they have, all approved drugs, and we compared this with everything we know on a molecular profile of disease progression. So maybe you are asking yourself, why do we do this? Well, we believe that looking at this, we might find new candidates for drugs or drug repurposing. And here is one example. We have endometriosis. If you just look at endometriosis without looking at the trajectories, you will find 9 approved drugs based on a drug bank. However, if you look at the trajectories of endometriosis and then go back down to the molecular level and look at the diseases associated, and then look at the drugs from the drug bank and which diseases which genes they are targeting, we can find potential candidates which could be used to treat this disease. In this case, we were able to find 55 candidates. We are not telling that these candidates are like really useful and they could be used. However, they're still hopefully valid candidates to analyze them, to do some clinical trials, to try to understand which of them could be used later on. Also, we show that if we moved from this disease in isolation treatment and look at the trajectory level, we could treat patients better, and we could, instead of giving a patient medication like for each disease, we could optimize this a bit by treating combination of diseases on a trajectory level, and then hopefully treat patients with smaller number of drugs. I want to show you, before I close, one interesting example. Maybe I can do it here. So if we look at the alcohol behavior disorder, not because of the gala dinner, just because I have a nice example. So here you can see alcohol disorder, like dependency on alcohol, and all the potential comorbidities, some at the same time, some which are coming later, and then the drugs we found at the molecular level which could potentially be used to treat this disease. And then if you look at the molecular level, you will find ethanol. But would you use ethanol to treat someone who already has issues with alcohol dependence? I don't think it's a good idea. I don't think it's a good idea to do that. So we found many candidates, but in order to understand, do they make sense, we check at the PubMed how many papers is talking about alcohol dependence and ethanol. And apparently there are many papers. But luckily, looking at using some agents and LLMs, we were able to understand this better and to find the evidence that using ethanol to treat patients with alcohol dependence is not a good idea. So as a validation for all of these exercises I introduced, we checked how many papers talking about these drugs which are candidates and these diseases we found. And we checked how many papers is talking about this combination, but that's not a good validation, just that's a signal that there are researchers writing about this. So what we did, we look at the TX agent, that's open source biomedical AI agent built on Llama, and authors are claiming that it learned a lot about drugs. So we prompt this agent by asking, we found these candidates on a molecular level. Does it make sense to treat patients with these issues, with these drugs? And as you can see, luckily, our TX agents were smart enough to tell us, don't use ethanol to treat patients with alcohol dependence. Okay, with that being said, I have to just mention my lovely colleagues. Some of them are visualization experts, statistician, complexity scientists, and obviously medical doctors. And if you have some questions, I'll be more than happy to answer. Thanks so much.
Questions?
Over there.
Thank you so much for the presentation. From what I understood is that you use molecular data networks just to validate after you get your trajectories. And my question is, have you tried and why you don't use it during the training, to have some graph-based prior that you can actually enable biology to guide your prediction? If you understand the question.
Yes, yeah, I definitely understand it. So the whole project started as a group of mathematicians and data scientists without understanding biology and medicine enough. So we started slowly, step by step, trying to extract some knowledge from this awesome data source, doing it step by step. And then later on, when we learned that we can extract something meaningful, we decided to go further and then look at the molecular profiles. And you're right, now we do have students starting from the beginning, using all of these data sources, enriching a knowledge graph, and then trying to understand what's going on. But this was more like a step-by-step process.
Maybe this can be discussion for later on, but just one more question. From what I know, PPIs are really biased towards some well-studied proteins.
Yeah.
How you deal with this?
Yeah, so this literature bias is really known, and then we see it. I showed you in some of the plots that all of these databases suffer. Some suffer more, some less. However, combining all of them, we managed to I don't know, at least have a smaller effect of the literature bias is obviously there. We won't overcome it, but at least it's a good news that if we combine many of the data sources, this bias is a bit smaller. Yeah. Thank you.
Hello. Yeah. Thanks for the presentation. I have a lot of questions, but I just put one. So when we are talking about patients, they usually have a lot of data, you have their blood tests, which are hundreds. So you have this huge space. How do you deal with that?
So we do have lots of data. That's very true. However, we are really slow in allowing researchers to use all of these data sources. So in this project, we don't have such a rich data source because it's on a whole Austrian population. However, we now have projects where we have more rich data sources, like we have PET CTs, MRI, blood tests, histopathology tests. And then in these projects, we use more multimodal approaches. However, these projects are ongoing and we don't have results to show. And these are more exciting than this, yeah.
Let's go here first because you're closer.
Hello, thank you for the talk. You mentioned that you were using LLMs to check the statements about uh, ethanol, etc. And I know there has been some problems with LLMs fact checking. So I don't know if you.
Obviously, no, I'm absolutely aware that this is not good enough to be validation, just one layer of validation. This project is under revision, and what we are doing now, we are also checking trials, like official documents and trials, to validate it with facts, not using just LLM, which could also hallucinate and everything. But yeah, it was just like one exercise to have one more layer of some kind of validation, knowing that's not good enough, obviously.
Okay, thank you.
Thank you for the talk. So people say that we have a huge bottleneck in the fact that hospitals don't easily share the data, and so we just don't have it for the research. So so in your opinion, how severe this bottleneck is, and what can we do to improve it?
Yeah, absolutely right. There's a huge bottleneck. Like healthcare system is one of the biggest sources of data. Like they're producing so much data every day, every minute. However, because data is really sensitive, also these data sources are quite sensitive on a patient level. But slowly we are getting there that more and more data sources is available. For instance, in Austria, at least at our university, we get access to all data, like all available data we can get. We just pseudonymize it, remove like identifiers like name and date of birth, and we can use it. However, these silos are really like isolated. So I'm learning on Austrian data, and I don't know if this is like something general or Austrian. But I think slowly we are getting there that more medical data is available, and it's like across centers, across countries. In the last 2 years, there are a few really good papers, one in Nature, where they develop a project on the UK biobank and Danish data source, which was like a really good sign that we are going in a direction where we have access to data sources from different countries.
Thank you.
Any more questions?
Thank you so much.
I have a question.
Oh, okay.
Don't be so quick. Return to the presentation.
Sorry?
Can you return the presentation?
I can return. Yes?
Go back to the slide with the ethanol.
That was an app. Okay.
Okay, so what is cocaine medicine for?
I'm not the right person to ask that.
Okay, thank you.
Thank you so much. Thank you so much. We can further discuss over a coffee. Thank you.
Thank you so much, Elma, for the amazing presentation and for stepping in at the last minute. It was truly amazing to have you talk about AI for medicine with us. And maybe as a remark to what Suat just said, you know, I know this because my father's in the hospital now. They use morphine for pain-killing properties, and that's basically, heroin is basically a derivative of that, right? So, you know, I think there's some connections to be made there. Okay, so for our next block of presentations, it's something that we find really important in the EEML community. Obviously, we try to bring as many people to give you these talks throughout the week who have connections to the region and who at least came from Eastern Europe or have strong ties to it. But ultimately, a lot of our speakers still hail from Western countries, right? And we don't really want the message of EML to be, you need to move away to the West in order to make impact. So one of the very important things we try to do every year is give a special spotlight to some very interesting, influential research that has completely originated and been incubated in the region. And today I am very pleased to announce that we will have 3 20-minute presentations talking about completely locally incubated research successes. We will first have a talk from Alexander Plamenets, who is one of the Maya members based at the University of Montenegro, who will be talking to us about anomaly detection. Afterwards, we will have Isidora Stankovic from the University of Montenegro, who will be talking to us about spectral analysis of directed acyclic graphs. And finally, we will have Magnola Zanelli from the Alexander Moisiu University in Durres, talking to us about coastal line monitoring with virtual and augmented reality for the port of Durres. These talks will be one after another. The speakers have agreed to quickly switch from one another to keep things smooth, and there will be no dedicated Q&A. You will have a chance to talk to them after the presentation. Okay, so without further ado, Alexander, if you're ready, please take it away. Thank you.
Well, so can you hear me? Does this work? Perfect. Okay, so hello everyone, and thank you very much, Petr, for your nice introduction. And I'm hoping that you're having a really great time here with us at Cetinje, and I would like to use this opportunity to thank you once again for coming and to let you know once again that we're very proud that we are part of the event, and hopefully you're learning something very useful and very good for yourself. So just a brief introduction about myself. I'm actually a teaching assistant and PhD student at University of Montenegro at Faculty of Sciences and Mathematics. I'm also a regular full member of Montenegrin AI Association, and I'm one of the co-founders and AI lead at a startup called Peito that actually utilizes AI to analyze online discourse and bring you trends from the outside. Yeah. So what I will be talking today is are parts from my research on the PhD, and with only a few words, I can say that it's actually the anomaly detection. And I would paraphrase Stephen Hawking here, saying that it's actually an observation that seems generated by different mechanism than the rest. It's like when you speak about it, it's very intuitive. But from the machine learning side of view, for me, it was very interesting because it's not an ordinary task. If you're defining something as anomaly, that means that you usually do not know how that looks like. Whether is it a value, whether is it a text or any kind of data instance, you usually don't know how does it look like. So actually you're not doing the detection per se, but what you want to do is to model the normal. Like I want to learn what normal is, create, let's say, some kind of space of normal. And then if I have another instance, if that's far away, then I can call that an anomaly. But also it's interesting because like if anomalies start piling up, is that an anomaly anymore, or it's some kind of a novelty or a new trend? So there are very much different, let's say, directions that you can use this. And from that point of view, for me, it was very, very interesting to take a look at. Just a brief introduction about anomalies themselves. At least from what I've found, you usually have these three types of anomalies, and they're point, contextual, and collective. Point anomaly is something that usually has a lot of literature, has a lot of techniques, because it's also the easiest task. What's the idea behind? If you take a data observation or any kind of instance, it will be anomalous every time. Like I'm having this admissible range of values, and whenever I find this value, it will always be anomaly. For example, in the sea of good comments, whenever you find something that hates speech, that should be anomaly. For example, 200 degrees weather is always an anomaly here at the Earth. So that's something that we can call a point anomaly, a single instance that you can always define as anomaly. From that gets a little bit tricky. Why? Because the second step is I have a contextual anomaly. That means the value as itself is not an anomaly, but it's anomaly due to the context surrounding it. For example, today will be 30 degrees in Cetinje. That's completely normal. But if that happened in January, that will be an anomaly because it's not really hot that much in January. Also, from, let's say, a heart monitoring point of view, if your pulse is around 160, that's pretty normal if you're running, but that's terrible if you're sleeping. So that's where we see, okay, context gives the value if something is anomaly or not. And usually the most difficult ones are the ones that we call collective anomalies, where if you take a look at here, each of these can be anomaly as itself, but also if you look at them together, they're anomaly surrounding their own context. That means I have some, let's say, an array of instances that altogether can also be looked as an anomaly. And these are usually the most difficult to find out about. For the anomaly itself, I will speak to you about two, let's say, different parts where I have tried a few different approaches regarding my research. First will be in textual domain, and the idea was to actually detect hate speech. The second one would be hard work monitoring and anomalies in that part. Our concrete use case here was to try to moderate a local news portal. And what was the idea? It actually started as a master thesis a few years ago. And we got some data and cooperation from a local news portal, and our definition was really simple. Let's define the anomaly as hate speech. I don't know if you maybe see the problem there. We have seen it really soon because hate speech is actually not an anomaly. It's like we were so naive to think, okay, there must be a situation where hate speech is rare, but oh, no, that doesn't happen. I will show you the data. Like this is from 2021 all to the start of 2025. So more than 200,000 articles and almost 4.5 million comments. Almost 40% of them were banned because many of them contain some kind of hate speech. And if you take a look at this black line here, it's like the ban rate, and you can see it's pretty stable with few spikes. But we have found out these spikes usually happen when there's some political event around. So that's like the general situation. And we said, okay, does it make sense to try to solve this with anomaly detection problems, anomaly detection techniques? We tried it anyway. And besides that, we had other problems. What are the problems? Besides data being unclean, that's okay, that's pretty solvable. You can do different pre-processing and so on. The biggest problem for us was moderator bias and error. For each of the comments that we got, we had the decision of the moderator. But we started training, we see results terrible. We were constantly looking, what are we missing here? And then we inspected the data a little bit by eye. And then we have found following. There are a lot of comments that were perfectly fine, but were banned, probably because of the error. And then bias was the other thing. Like if I'm, for example, cheering for Boca Juniors and I see a good comment about River Plate, I unintentionally ban this because I don't want that to be seen. So there were so many problems, and we said, okay, actually we cannot do anything with this. Let's try to build the ground truth so we can try actually something meaningful. And what we decided to do, we took 5,000 comments from the original data set in the same distribution as it was regarding the allowed and the banned category. We created a custom web application and gave that to the professional linguist. I will also mention and thank to Mrs. Živković for annotating all of those comments. She is working at the University of Montenegro and Faculty for Languages. So said, okay, we need to have a different approach. We need to annotate this in order to try something and at least see if that can work. And we have, after that, tried to implement some techniques. And you can see those in the down are anomaly detectors. And the one in the up, logistic regression, was actually a classification task. So as you can see, the anomaly detectors performed terrible. They were really close to actually performing as a model by chance. Why that happened? Well, we see that there are two reasons for that. Like if you're doing an anomaly detection problem, as mentioned, you would usually imagine some space where normal is somehow connected. And then the anomaly is either a point or a tail, something that's close but on the outside. In our case, where you have 40% of the comments on the different class, those places, those spaces are really intertwined. So anomaly detectors cannot really learn them. That is the first step. The second step, where the actually models shifted, they classified shorter comments as more anomalous. And therefore, we have missed the context completely. But the one that was actually performing well and is our official, let's say, starting point was the logistic regression, which gained a score of around 0.8. 0.85. So for that, we completely abandoned anomaly techniques and decided to continue on the classification task itself. And our next the diagram will show what was the idea, what is like the last implementation of this. We start from 5,000 comments, and we use Bertic and Condor, which will actually embed those comments for us. After that, we decided to do stratified split, which will also preserve the class ratio. Afterwards, we do fit logistic regression, and we have received the result of 0.85 here. Our next steps here for sure would be, and we are working currently on that, to fine tune Bertic for this kind of classification with some different tryings like XLM language model, which is actually a massive multilingual baseline, and HateBERT, which was originally fine-tuned for abusive language but works on English. I didn't put any numbers here as this is still a bit work in progress, but for now, as we can see, for South Slavic region, of course, Bertic is still the best, and you lose the most if you try to do translation. So if you translate, you're actually losing too much of a context, and that doesn't work. So with that, I would conclude this brief introduction about the textual part, and I will move to the part of detecting hard anomalies. So this is right now also part of my research, but actually started as the proof of concept project at the University of Montenegro. The idea was to find a suitable sensor which can track ECG recordings of a patient and try to find anomalous events or any kind of disorders. What's the trick here? Well, those sensors always give you totally different electrocardiogram data than if you go to a clinic. If you go to a clinic, you can see, let's say intuitively, you will see 12 lines of this type, which are monitoring heart from every position. And if you're using sensor, that's usually only one lead, only one channel, only one line. So you're already losing a lot on the information. But it was interesting to see what can we do and how do we work with it. The device that we chose is the Polar H10, and you can see it here on the top right. It is actually a strap. So you will strap it around yourself. It says around here, and it will provide you constant monitoring for something similar to one of the leads in the clinical ECG. What's good with this device? It has its own SDK. It's affordable, and then you can easily program it to retrieve the data, which we did. We created a mobile application that actually retrieved data for us, stored in a big data system. And we already said, okay, we have some experience from the textual layer. Let's already try to annotate something and already try to build at least something for ground truth, because we were only recording. We didn't have the labels as such. So we also created an application that will show one channel to our doctor. And I would also like to thank our colleague Banyac for annotating these ECG channels. And we have 1,520 annotated for now. The idea is, of course, to expand that and to try to, what we found out in the next slides, to also validate that on a much larger scale. Why was this created data set interesting for us? Because amongst 1,500 recordings, there were 22 cases of something that's called atrial fibrillation. I don't know if you have already heard about that, but it's a specific condition which disorders the rhythm of the heart. What's tricky about it? You may not feel it, but on the long time level, it will actually destroy your health and your heart. So it needs to be dealt in time. What we wanted to do, okay, we wanted to extract features either from signal morphology and for beat morphology, and tried one-class models like Mahalanobis, isolation forest, and one-class support vector machine. There were some results that I would mention. For us as a start, all of these models were around 0.8, which is not bad for such small data set and as a starting point. But I would like to mention more what you see on the top, and that's something that we call P-wave consistency. To actually understand what's going on, let me show you a synthetic example of normal ECG and ECG that has atrial fibrillation. Whenever you're inspecting ECG, you're looking at these several, let's say, letters, which designate parts of the heart function. This P is preparation, then you have the heartbeat, that's something that's called QRS, and then you have T wave that slowly leads to relaxation of the heart and preparation for another heartbeat. What clinicians say us are the following. You detect atrial fibrillation with irregularities from these RR intervals. You see here is like this one, here is bigger, then it's again different, and so on and so on. But also you can detect atrial fibrillation if this wave, this preparation is either missing or it's not regular. What are usually edge devices doing, especially those using PPG, they're only looking at RR intervals. With our result, we have seen that at least on this device, you can also count on P wave consistency, meaning that it will probably improve the atrial fibrillation detection if you, besides RR irregularities, are also looking at the P wave, because we see a strong correlation with this device and the atrial fibrillation. And of course, as this is not a big sample and not tested, we can say that it's very useful for triage and for monitoring, but right now not for diagnostics, as it would be needed to be validated to a much larger data set and much larger testing. Yeah. Besides that, we wanted to try one more technique. Okay, we have only 1,500 of annotated examples. That's basically nothing. And we want to say, okay, if I'm having a data set that has really low amount of data, can I try to learn from something that has a bigger amount of data? So we took this data set that's called PTB-XL. It's open source, you can download it and use it for research purposes. And I would recommend everyone who wants to take a look at this kind of data to try. It's a clinical data set with around 22,000 recordings annotated by expert physicians. And it's totally different than our data set, because there we have 12 channel. On our data set, we have single channel, and we wanted to ask ourselves, can I learn something from there and embed it into our system, at least to try to improve what we know already? And the idea would be, okay, pre-train on the PTB-XL, pros and get something from that, then transfer onto your data set and see if that improves anything. And I will now, for me, it was easiest to actually show you this via a few diagrams. I will now explain you what was our idea. As you can see on the left is the signal that we have from the PTB-XL database. And that's clinical ECG, 12 channels, heartbeats, and so on and so forth. We firstly did inspection with, of course, our doctor who helped us. Which of these leads is the most close to the one we have from the device? And that's something that's called lead 2. I won't go into so many medical details as we don't have time, but I will mention once again, as Peter said, later after the session, I am really open for drinking a coffee, or if you can, we can also drink beer. I know the dinner was yesterday, but I think we should only continue. So I'm taking lead 2, and then as they are sampled with a frequency of 500 Hertz, we are downsampling that to 130 because this frequency is actually from the device. So what we already wanted, okay, I will take that and I will reduce it to the type of data that I have from the device. And from that, we do the training. So the base was residual convolutional stages, all together with fully connected layers and the 5 classes that we have from the PTB-XL. Later on, you get a vector of 256 dimensions and pre-trained from the PTB-XL database on this way. Afterwards, we say, okay, let's try this approach. I will completely freeze convolutional layers and their weights and try to bring our classes. I didn't mention that, but I will now. We had the different classes from the PTB-XL dataset because simply some things that you see on a clinical ECG you cannot see here. So we put on the right our classes, we froze the convolutional part, the residual networks, and we pre-trained this part. It was firstly randomly initialized, then trained on the data and so on from our small data set. And that was first 20 epochs, and then in the next 20 epochs, we just unfreeze everything and train for the 20 epochs more. And that was the idea to like try to transfer some of the learning from the PTBXL to the our data set. And that actually worked pretty well on our data set, as we managed to recognize norm class with really high F1 score. And besides that, we got really high score again for the atrial fibrillation. This actually supported our initial proposition that you can learn from the completely different data set if the problem is at least similar to each other. Yeah, so thank you so much, and I'm hoping that you enjoyed this part. Thank you. So I would say once again, I'm really happy to grab a coffee or something else, and let's talk afterwards in more detail. Yeah, thank you. Yes.
Okay, hello everyone. My name is Isidora Stankovic, and I'm coming from Faculty of Electrical Engineering at University of Montenegro. And as we said already, I will talk about spectral analysis of directed acyclic graphs. So first of all, I want to say that I'm actually coming from signal processing theory, moved then to graph signal processing. So I will try in the theoretical background to try to familiarize with the machine learning terminology and the signal processing one. So later I will move on to the zero padding on DAGs. This is actually our work which we are doing. Later, of course, some summary. So first of all, why we bother about spectral analysis on DAGs, on direct acyclic graphs, is actually because DAGs are everywhere, even in machine learning. So for example, computational graphs, causal Bayesian nets, autoregressive models, they're all kind of a graph. So the key tool to find frequency, to find the spectrum, is actually doing the graph Fourier transform, which is actually the basis for spectral GNNs and graph filtering. But the problem we have with DAGs is that the adjacency matrix is actually nilpotent, which means that the eigenvalues are equal to zero, which means that the GFT actually collapses there. So the work we are doing is actually called zero padding, and I'll explain to you a bit more about what we mean with zero padding. And the idea is to restore the spectrum without you losing the output of our filter. So just a little bit of the terminology. What we mean with a graph, so we have a graph of n vertices, and it is represented with adjacency matrix. So the edges are connected, so the values of the adjacency matrix are equal to 1 if the vertex m is connected to vertex n. And when we talk about graph signal, we mean only a vector of the values on those vertices. So here is actually an example of a DAG, and the values which are on the signal on the vertices is actually the graph signal in our case. The main operation in graph signal is actually the graph shift operator. In the directed case, we mostly use the adjacency matrix for our graph shift operator. And for example, a graph system can be modeled as a polynomial of, for example, the adjacency matrix in our case. And this is something which is also familiar to you. It's actually the graph convolution. So when we do the propagation in the graph, it's actually the message passing. So for example, AX is one message passing hop. And for example, we have those coefficients HS, which are actually the coefficients which the spectral basis GNN try to learn. The main problem for if we talk about the adjacency matrix, in most cases, the adjacency matrix is diagonizable in most graphs, but we'll talk about that also a bit later. So when the adjacency matrix is diagonizable, we can find the graph Fourier transform by doing the eigendecomposition of this adjacency matrix. So this stands for most of the graphs, but not really for the DAGs. So first of all, what we mean by DAG, the name says it all. So we have directed acyclic graph, which means that it's directed and there is no cycles in it. Here is also an example of a DAG, and why they are interesting for us. It's when we do the topological ordering of the vertices, you can see that its adjacency matrix is actually strictly upper triangular. When the matrix is strictly upper triangular, for us, that means that the matrix is nilpotent, which means that the eigenvalues are 0, which I already told you. And this is something also which is familiar to you. So the strictly upper triangular matrix, it actually has some kind of a structure of a causal attention mask. So it's something which can be useful even in the machine learning space. When we have the eigenvalues which are equal to 0, that means that actually the graph filter also collapses. So the graph filter will become only, will collapse to the signal gain of H0, which means that we don't have the graph modes. So all graph modes are identical in that sense, which means that we don't have spectral components, so they are indistinguishable between each other. The frequency ordering, of course, disappears, and there is, we cannot interpret our frequencies. What is interesting here to note also is that in the vertex domain, actually, the propagation is still there. So it's still existing and still meaningful, but finding the frequency in the graphs, in the graph signal, is really hard. So because we cannot do the frequency interpretation of them. Of course, this is not something which is only our group doing, because it's a general problem of DAGs, because there are a few groups also who are doing that. So we can part them into two groups. So the first group of techniques to find the spectral content in DAGs is actually trying to change the basis. So for example, maybe some of you already heard about Hermitian Laplacian. So what they do is actually they abandon the adjacency shift. What does that mean? Is actually they do some new domain. The new domain actually tries to not totally, but they lose the directivity also of the graphs. So the new domain is actually hard to interpret in the sense of looking at the spectrum. The second group is actually adding edges to force diagonalizability, which means that they will actually change the graph, and that means that we actually will change the output also. So both of the groups actually alter the problem of the physics of our problem. So our idea and our goal is to keep the adjacency-based GFT, but not to change the spectral output, so not to change the graph output of our system. So one of those examples, here you can see actually, so we have a signal, a graph signal of n vertices. In our case, here is a path graph, a directed path graph of 8 vertices. So of course, one path graph is actually a DAG. As you can see, of course, is something which is familiar also to you. So of course, for such a graph also, the matrix is nilpotent, the adjacency matrix is nilpotent. So we don't have the spectrum, we cannot find the spectrum just by looking at it. But in this case, we actually find we have the fix. I mean, we have the fix from signal processing idea. So how we fix that in the signal processing sense is to use the basic discrete Fourier transform. So something which we know from signal processing and discrete Fourier transform is that the signal periodicity is assumed. So to do the DFT, we have to assume that the signal is periodic. So what does that mean in the graph terminology? That means that we'll actually add an edge between sink and source. So adding that, we make the periodic signal. So the graph will become periodic and cyclic, of course, but we'll explain that more. So when we do that, when we add the edge, now the eigenvectors are actually complex exponential vectors, which means they are now DFT basis vectors. Of course, here now we have the same, what is happening in the graph is actually the same as happening in the DFT analysis. So here we can easily connect those two, so the signal discrete Fourier transform and the graph Fourier transform in that sense. How does zero padding on DAGs go to that? Here, actually, I will try to explain the equivalence between the classical DFT and the graph signal processing and the graph Fourier transform. So, as I said, in signal processing, we have a signal of n samples. how does that equalize in graph signal processing? We have a graph of n vertices, and those values, of course, on the n vertices. As I said, in the second part, we assume periodicity, which means that we have a signal of n. It's periodically extended in infinitive so that we can find discrete Fourier transform. How do we do that? As I said already, we add sync to source so that we have the periodic signal also in the graph sense. But one thing we didn't mention before is that doing the DFT, the one thing we always do also in DFT is actually we add zeros. Why we do that is that we somehow avoid aliasing. Aliasing actually are trying to avoid that the first samples are not mixed with the last samples. So to avoid that, what we always do is actually have our signal of n vertices and add zeros. How many zeros we add? It's actually depending on the graph filter we are using. So if we do, for example, S hops, let's say in the machine learning terms, if we do S hops, we try to add at least S zeros also at the end of our signal. So this is how we do the DFT in signal processing. So what is the equivalent in the graph signal processing is actually not just having the edge from sink to source, but actually adding also vertices in between it. So here, what we're going to do, we will add at least S vertices, which are actually zero valued. So it's zero padding, but on graphs in this sense. So what we try to do with that, we have finally the same experience as we do with the discrete Fourier transform. So we don't change the output, but we can finally find the spectrum. Here actually, so as we said, now this is actually only working with the path graph, but we will talk a bit about that more. So one will actually now ask, why isn't it now, doesn't we break the cyclicity? Of course we do. So this actually what we did is cyclic on purpose. Why? Because we don't change our DAG. So what will happen now, the DAG is still there, the original DAG is still there, but it's becoming a subgraph, but we don't do anything with our DAG, we just add the analysis to it. So the big graph, cyclic graph, is actually now cyclic, but it's used only to find the spectral. Of course, the DAG is still staying where it is. It's just becoming a smaller graph in our bigger graph. So we still have our original DAG. It's still a cyclic bistructure. The original vertices are still there, but what we do, we just zero pad it so we can do the analysis. Of course, why we add the zeros is exactly because of that. So we don't change the output of our system. So the zero vertices will just delay the feedback so we can still have all our values. And the cycle actually restores, as I said, the spectrum. And of course, the output will be the same as our original one. So the zero padded one will give us the output when we have the original DAG. So here is, for example, one graph with 16 vertices. We work with an order with four system of order 4. So here we added 4 new vertices, 17, 18, and 19, and 20, which try to delay the feedback. And the main thing what we got here finally is that we have our eigenvalues lying around the unit circle. So maybe not exactly, but we finally have our eigenvalues which are lying on the unit circle, so we can actually restore our Fourier transform. The second part also here, as you can see, these are the eigenvalue of angles. They actually tell us, they interpret the frequency for us. So if the angle is, for the small angles, we have slow modes, so they are smoothly changing. So this is actually representing the low frequencies. And we have the ones which are rapidly changing, and the rapidly changing ones are actually our high frequencies. So from our eigenvalues and from our modes, so from our phase of the angle, the phase of the eigenvalues, we can actually find the frequencies in our case. So how we can implement in the graph systems? In the graph systems implementation, we can actually see that we have, for example, we have a graph filter of order S working with the DAG. So X for us is the signal on a DAG. When we do the graph filtering, the graph zero padding, actually the new system will work with a zero-padded adjacency matrix and a signal which is also zero-padded. But what is interesting for us that if we have a graph filter of order at most S, the output of, so the first n vertices of the zero-padded one will be the same as the output of the one which is not zero-padded. So this is the main achievement we got. The output is still the same. I mean, in the first n vertices, if we look at them, they will be the same as the output if we look in the DAG, looking from the DAG system. So here we have the output is preserved, the spectral domain is implementation is possible, and the original DAG is staying the same, so we don't change the dynamics in it. As I said before, this is actually working perfectly for the path graph, because the path graph gives us the analogy to discrete Fourier transform. So we had to think about general DAGs. For the general DAG, we need one more step in between, which of course the path graph already has. So the step in between is actually connecting the DAG. So what we want to do is we have our general DAG, we start from our DAG, we try to connect it first. How to connect it? We try to make a Hamiltonian path. So we do a Hamiltonian path DAG, and then we will do the zero-padded augmentation. So first of all, as here it says, we add edges. So the Hamiltonian path, so one Hamiltonian path is possible. In the second phase, we pad each of these edges. So not just the ones synced to source, but the ones we are adding for the Hamiltonian path. This is actually going to make the spectrum for all in general case of the DAGs. Of course, one will also ask, of course, we will add more edges and more vertices, but the change is smaller. So it's a modest and a linear change, so addition to our original one, knowing that after that we can actually find the frequency. So it's I think, a better cost than anything else before for other groups. So how does it always work this way? So to find the Hamiltonian, find the Hamiltonian and then zero-pad it. We tried, of course, we were working only on the smaller graphs, like 7 and 8 vertices, because we wanted just to be sure that it does work. So in those cases, where we talk about graphs of 7 vertices and 8 vertices, we did a lot of graphs, and we tried to find if they are diagonizable, all of them. And as you can see, in most cases, in 98 or more cases, we could do the spectrum, we could find the spectrum. For the other remaining ones, we can do the weighting of the edges. But of course, this is one of the things we are still working. I mean, we did work, and still something which we could work. How to make it 200, hopefully, but probably not always 200, but at least to get it even better than now. So one of those ways is actually to do weighted edges instead of just adding edges. But the main thing right now is that it works in many cases, in more than 98%. And here is this example of the general DAG. Here we have a DAG, as you can see, 8 vertices. The big ones are the original ones, and the blue edges are the original edges. What we have to do, so here we work with the system of order S equal to 2. And first of all, as I said, we first have to make the Hamiltonian path. We make the Hamiltonian path connecting vertex 2 to vertex 3 and vertex 5 to vertex 6. We do that first, and then of course we do the going back to sync to source, because we need it for the periodicity. Second thing, we said we are padding all of them. So first 2 to 3 we padded because we work with orders of 2. We pad them with 2 vertices, the same from 5 to 6, and then from 8 to 1, of course, 2 more vertices. What we get when we do all of that and try to find the spectrum, we have here, as you can see, the eigenvalues are lying around the unit circle. So good results for us. One more thing we have is when you look at the frequencies, they are really nicely the frequency index, so the one angle of the eigenvalues are giving a clean and monotonic change, so we can easily see which ones are the low frequencies and which are the high frequencies. So one of the applications we can do here is how to filter a graph, so how to denoise a graph. One thing we, of course, we achieved is having the diagonizable adjacency matrix. The new matrix will be, of course, the one which we connected and padded. And we try to denoise a graph. How we do that? We try to find a desired spectral response we want to get. So we try to get our filter coefficients HL to be similar to the G, the one which we are trying to get. Once we get the coefficients in the spectral domain, that's the main thing. So we are trying to make the coefficients, to find the coefficients in the spectral domain, and then we do the denoising actually in the vertex domain. Because why we do it in the vertex domain? Because, as I said, we work there with our actual DAG. So it's less samples than using the big one, the spectral one. So in the vertex domain, we do next the part we need. So we take the n coefficients, and we can do the filtering. I'll probably better explain it if you see the example. So here, for example, on the left, we have the original signal, lying on the zero-padded DAG. So you have the values of the nodes here. So here's the clean one. Then we have the noisy one. You can notice that we have the ones that some of them are changing. So you can see the red one there also. So different values. We don't have here written the values. The main point is just to see that it's noisy, of course. Of course, we have, because it's a zero-padded DAG, we have the one which is synced to source. So this one is not changing, of course. And as you can see, by doing what we just saw, we get the filter signal. So the filter signal looks similar to the original one, which is actually the main point here. So from the noisy signal, we started with an SNR of minus 6.99 dB, and we came to the filter signal, which is actually SNR of 6.21 dB. So it's a pretty good denoising actually in that sense. But it's a small example just to illustrate what we are doing here. So just a little bit about what we are talking about. The first thing you need to come from this presentation is actually that DAGs cannot be, the spectrum of the DAGs cannot be found easily. So because the A matrix is nilpotent and we cannot do the GFT. So one of the ideas, what our group is doing, is adding sync to source and to do the zero padding. And so far, it showed us good results. Of course, we are working more and trying different ways of finding the spectrum in that sense. So, but the good thing is that the spectrum is restored and the output is preserved, which is the main thing for us. And we saw one example of the filtering of DAGs where we got the denoising part very good. And of course, hopefully in the machine learning part also, it's a usable spectral domain for causal and attention graph structures. So thank you very much, and I'll give for the next one.
Yes, yes, of course.
Hello, everyone. I'm Manuela Zanelli. I come from Alexander Moisiu University of Turas. I'm an assistant lecturer. First of all, I want to thank you all the organizers for giving me the opportunity of being here. Also, I want to highlight that I'm very happy that I see all the students that in this peak time of summer, they are here attending all the lectures and being very eager to know the trends of the technology. For many years, I've worked in industry, and I'm saying this because my research is related with the port environment. And the last years, I stepped in academia. My research is on digital twins. I don't know, maybe some of you have heard of them, the others not. So first of all, I will give a short intro on the digital twins, and then I will pass in my research on the coastal environment of a port. So what is a digital twin? A digital twin is a virtual prototype or a virtual model of the physical asset. What are the main parts of a digital twin? Is the virtual prototype and the 3D model. So this is the anatomy of a digital twin. It has the sensors where it gets the data integration. The main technologies that are used in digital twins for the integration of the data are cloud technologies, also AR and VR technologies. Related to cloud technologies, the main tools that are used are Microsoft Azure Digital Twins and Microsoft Azure IoT, and also Google services are used also, and many AWS services also. The virtual model is the 3D model, hydrodynamic representation of the asset. There are some algorithms, ML algorithm for creating the predictions that are used in digital twin, and then the feedback loop. Digital twin maturity from visualization to active, it is descriptive. So from it visualizes current state. Informative, it diagnoses and explains dashboards. Predictive, it forecasts in different scenarios for which it used. And then autonomous, that gives some feedbacks if the digital twin is active, because there are two ways in which we use the digital twin. We have passive digital twin, that is one way, so we get the data from the sensor and we visualize the data, but we don't get feedback from all the data that are operated. And active digital twin is a closed loop, so it gets the data, elaborates the data, and then turn back feedback from the actuators to take decisions on the situation that is created. Where are the fields that the digital twins are used? Mainly in manufacturing, in smart cities, in healthcare, and in aerospace. So the research is enhancing coastal line monitoring in maritime ports using virtual and augmented reality technologies. Sorry. There are used 4 scenarios for some situations in port, like storm surges, coastal erosion, rising sea levels, and fragmented monitoring. I have used these scenarios because for these scenarios, it was easy to get the data since the port has all this data from different systems that it used. There are some examples that I've taken for different ports that have implemented digital twins. Nowadays, all the ports are very eager to implement digital twin because they help a lot. But each port is implemented second the necessities they have. For example, Port of Rotterdam is implementing on climate risk monitoring, Port of Hamburg in flood forecasting, waste sensor, GIS mapping. Port of Singapore is one of the best application of digital twins because Singapore, I don't know if you have heard also, has done all the city digital twin, including the port. Antwerp Bruges is for tidal forecasting. Port of Gothenburg is for oil spill. Norwegian Coastal Authority is for live drone feeds. And some small achievements are also done in Port of Tours due to a project that it was included, IoT project, where is done a virtual prototype for the energy consumption in Port of Tours. System conceptual architecture, the 3 main layers of the architecture of digital twins is data acquisition layer, that are the data that are taken from the sensors, or the historical data. If the digital twin is the passive one, we use historical data for creating the virtual prototypes. Digital twin core, data fusion and hydrodynamic modeling, ML algorithms. The algorithms that I have used not only in this research, but in other research also, is long short-term algorithm. Is the best algorithm that is used in digital twins because has plain and consequent data, so it works best for digital twin and AR and VR visualization. The methodology sensing to decision is sensor installation, data integration, digital twin modeling, AR, VR interface, and predictive analytics. In this research, the sensor installation, I had already from the installation in the port environment, so it's passed, but the other steps are included in the research. This is the operational cycle that is taking the data from the sensor, data fusion integration, dynamic digital twin updates, immersive technology, predictive analytics, and creating all the cycle. This is the idea how the system will be from modeling with VR technologies. So this is the main view of the app. Then we have the different scenarios. The first one is storm surge. The second one, multi-user emergency drill. The third is erosion and live dashboard sea level. From all these sensors, they are created from the views that are real views of Port of Douros. Also, the data, as I told, are taken from the systems that are in Port of Douros. But I have to stress in this that the digital twin is used only for getting information. It's not included the actuation part. So we get information from digital twin and then we operate from the other system or from the manual operators that are in port, second the scenarios that are used. The benefits for the Port of Douros for using this is faster response, cost saving, improved safety, environmental monitoring, and green transformation, that is for energy consumption. Challenges, data reliability, technical expertise. It's really difficult for the moment to find technical expertise for digital twins, especially in Albania. Connectivity, real-time updates, demand fast, resilient. Either Port of Douros has very innovative technologies in many systems, but there are some gaps that should be filled in order to create the whole workflow to be fluent and to work in real time. And cybersecurity and governance, that is very delicate at the moment because all the data are very important to be kept safe and not to, especially in digital twin, that is very related and very sensitive to the data. So for this research also, I've taken the data since the Port of Douros was part of the project. That's why I had the possibility to take the data. For future research, dynamic digital twin dashboards, cloud technologies are integrated, but not fully integrated. For example, cloud technologies for digital twins should be bought in a separate way. They are not part of the whole packet of the Microsoft services. And regional level digital twin networks for interport maritime safety. Conclusion, digital twin and AR/VR provides a revolutionary approach to coastal monitoring at Port of Douros, fusing real-time sensitive, predictive analytics, and immersive solution. Thank you for your attention.
All right. Thank you so much, Magnola, and thank you so much to Alexander and Isidora as well. I hope this serves as a clear signal that we can do amazing research with real impact without leaving our region. So I hope this inspires you to think about what you can do within your communities to make similar kinds of impact. We will now take a 20-minute coffee break. I will ask you to be back here at 11:50 sharp. We will have a fantastic talk on efficient machine learning and AI from Dan Alistarch at IST Austria and recently Anthropic. So hope to see you there soon. Thank you.
So we'll be starting soon. So if people can come into the room and take a seat. Not sure how many are still at the coffee break, but. Okay, so if everyone could take a seat. Okay, cool. Yeah. So, okay, we'll just start. So it's my great pleasure to introduce our next speaker. I know Dan for a very long time, which means I need to be very careful what I say. So actually we did our undergrads together. And I remember staying up all night with him doing homeworks. But yeah, after undergrads, Dan went to APFL where he did his PhD, then a postdoc at MIT. He was for a while in Cambridge at Microsoft, and then moved to ISTA next to Vienna, where he's been a professor. And recently he's doing a sabbatical at Anthropic. And he's been doing a lot of amazing work, particularly in the space of sparsity, quantization, generally optimization of neural networks, and so on. And today he's going to talk us about computationally efficient learning. And with that, Dan, I'll leave it to you.
Yeah, thanks a lot for the invitation. Thanks a lot for the very nice introduction. So I was at dinner last night, so I think I just wanted to kind of continue the momentum a bit, and I wanted to start with a continuation of the quiz because I think people enjoyed it quite a lot. That's what I heard, at least. Okay, so the first question is basically what is the bitter lesson? And we have three options. One is rakia can really hurt the next day. The second thing is don't eat bitter Ivar. And the third thing is something about the importance of computational efficiency for AI methods. And does anyone have any ideas about the right answer? I mean, all three things are actually correct, and they're very important at different stages in life. But the one I am going to focus on today is this quote, which says, the biggest lesson that can be read from the previous 70 years of AI research is that general methods that leverage computation are ultimately the most effective and by a large margin. So does anyone know who said this? Rich Sutton, yeah, that's right. So he's the Turing Award winner, co-inventor of RL. So today I'll try to talk a bit about why this is so, and I'll try to give you a couple of examples. So like the case study, I think probably the best case study we have right now in ML is generative AI. So this is among the most rapidly adopted technologies in history. If you think about the number of people, like the progression of the number of people who are actually using this technology. And it's kind of interesting that it's really a great way of bringing computation in a data center to the masses in a way that people can actually sort of experience day to day, right? So I think ChatGPT had recently announced that they finally have 1 billion weekly active users. So to understand what I mean by massive usage of computation, like we can look at this graph, which depicts the increase in compute necessary to train a state-of-the-art language model over the past 5 years. This is based only on publicly available data. And you can see that it's been going up by about 50,000x. It doubles roughly every 3 to 6 months. Again, we don't have the closed lab details here. And then for inference, it goes up by about 300x, basically every half a year. At the same time, if you look on the orange line, that's the capability of a state-of-the-art GPU. So basically the most powerful single device for computation that humanity can create right now. These are NVIDIA GPUs. And you can see that basically these have only increased over the same 5-year span by about 20x, okay? So this literally gives you a gap of 2,500 between what we need and what we have, okay? And the gap is being closed by these things, which are popping up pretty much everywhere, mostly in the US, but now also in the EU. These are massive data centers which hold literally like enough compute to fill the gap. So essentially, I think this data center has about around 50,000 GPUs. This is the XAI data center in Memphis, Tennessee. And this is actually fueled in part by natural gas turbines, which certainly isn't great for the environment. So this is an illustration of kind of the bitter lesson in action in some sense. But it also tells us that it's really important to be able to reduce these costs, so essentially improve the gap by reducing sort of by improving the efficiency of AI, because now this is kind of for real money. So it's no longer something that we care about just in a NeurIPS paper. It's something that might actually reduce the amount of pollution that people in Memphis experience every day. Okay, so it's interesting to see how we got here, and this is basically I'm going to go drill down a bit into how is the bitter lesson relevant to LLMs. So it's all to do with this small rodent that's called a chinchilla. I don't know if any of you has ever seen one. So basically, the key sort of concept here is scaling laws, which are essentially physics types sort of interpolation approaches, which allow us to predict large-scale model performance from smaller scale experiments. And the reason why the rodent is relevant here is because Google and GDM, in their great wisdom, decided to call these the chinchilla scaling laws. I think this was because it was following Gopher or something like that. So it seems somewhat random, but people call these chinchilla laws. So basically, what does this mean? The law looks literally like this. So your expected evaluation loss for a model that's being trained on over n parameters for d amount of data should be roughly a coefficient a over n to the alpha plus another coefficient b over d to the beta plus e, where a, b, alpha, beta, and e, these are basically parameters that you're able to fit, and e here is your irreducible error. So basically you assume that your data set has some error that you're never going to be able to remove, okay? So the meta algorithm here is that we take small LLMs, let's say GPT-2, and then we fit these constant parameters at small scale, and then we are going to use this to extrapolate performance at larger scale as we increase n and d. And what you get, and this is these are some figures from the original paper that kind of started the whole thing, from Kaplan et al. In 2021. They were fitting a slightly different type of scaling law, but I think the illustrations are quite telling. Basically, you always have test loss here for a GPT-2 style LLM. And then on the other axis, you either have compute or data set size or parameters, and these are basically log factors over here. So then the clear conclusion that you can draw from these are empirical plots, is that as you increase compute, as you basically increase compute by order of magnitude, you can continually expect to get the loss to be lower. Okay, so this is basically, I think it's a good instantiation of a general method, or like a kind of transformer being a general method that can leverage computation. Because I think that the conclusion that OpenAI researchers and then I think Silicon Valley investors kind of got from here is that if we have infinite compute, so if we take this and essentially we roll it on forever, we keep increasing the model size, we keep increasing the number of parameters, the number of GPUs in the data center, then we will be able to get something that's arbitrarily low error, or at least it will get to this E factor. Okay, so basically, the more compute you push in, the better the model you're going to get. Okay, so what does this lead to in practice? It leads to, and here again, I can only extrapolate on public data, so I just pick a couple of models that for which we have pretty much all of the details. So for instance, there was this Llama 4 Maverick model, which was a 400 billion total parameter model with 17 billion active parameters. This is an MOE architecture trained on 22 trillion tokens and approximately 6 million GPU hours. And then the larger model that was trained in the same run, I think this was stopped early because it wasn't going well. This is called Behemoth. This was 2 trillion total parameters, so 5 times larger, 300 billion active, and basically 30 trillion tokens of data. So you see, basically, we're just going over the x-axis deeper and deeper into this kind of lower loss territory. And I mean, Llama 4 wasn't a particularly great pre-train, but notice we literally have almost the same numbers for Kimi K3, which was released a few weeks ago, which is really state-of-the-art for open models right now. So basically, you can see that this march of ever bigger and bigger, it keeps progressing. Okay. So yeah, so these models really, I mean, we're at the stage where because these methods can benefit from more compute, people literally just push more compute into it. And it's kind of also interesting to see, like from the kind of society's perspective, it's kind of interesting to see how much does this actually impact us as kind of the whole world. And I think the only company that put out a reasonable study for this was Google. These numbers are a bit old, unfortunately, but this is all we have. And this is so this is a study by Jeff Dean and co-authors, and they looked at energy usage, carbon, and water per prompt. So basically, this is for Gemini 2.5, I believe. I mean, to be fair, this wasn't a particularly good model or a particularly popular one. So I'm not sure exactly what their numbers for 3.5 Pro are. My guess is they would be a bit higher. But there are a few very interesting findings in this study. So basically, per average query, so basically this is, I would say probably the median query is Gemini, please set an alarm for me for 9 a.m. or something like that. That's probably the median query is probably not very complex. So you have 0.24 watt hours, 0.03 grams of CO2 equivalent. So the authors here, they say this is about 9 seconds of watching TV. I mean, we'll maybe discuss this very briefly. And then it's 0.26 milliliters of water. So that's basically 25 drops of water. So, I mean, I think the point they want to make is that the computational usage, I mean, the computational usage or the power usage, these are not that high. And certainly this doesn't sound like it's going to remove all of the water from mainland US. But at the same time, notice these numbers, they do add up, right? So basically, if like one person watching 9 seconds of TV is not such a big deal, but 300 million people watching TV for 9 seconds each, that's a lot, right? So that's something to keep in mind. I mean, I'll just add for those of you who are maybe closer to experts in this area. So basically, this is full stack, so that's very good. So they actually took it all the way from the cable that goes into the data center, and this is per prompt attribution, and this is all across text, image, and so on. I mean, there are some issues here because they don't discuss the tails. So basically, you can have notice you can have very heavy queries such as DeepThink, which I would imagine are way beyond what's presented here. And then the carbon accounting choice is basically, it's kind of an average. It doesn't tell us how much they actually paid for, for the data center where this was run. This is basically some kind of equivalent taken across all of their data centers. And so one has to be a bit careful, but I think it's good to have these numbers in mind. Okay. So, but one thing that's kind of interesting is that they gave us these numbers at the end of like a major push to improve their data center efficiency, specifically for LLM kind of LLM serving. And they report that they were able to improve their median cost by about 32 times over the previous year. And about a 10x out of this 32x is actually due to optimizations that they call model compression, in particular quantization and speculative decoding. So today I'll try to explain, I try to give you some kind of understanding on the algorithmic side about what this actually means. And then in the tutorial later in the day, you'll actually do some of this yourself to see how you can actually improve the model efficiency for models that you might want to deploy. Okay, so that's the plan for today. So the first question I want to ask is, what is this model compression thing about? And one thing is that, so I mean, for me as a researcher in this area, I've been working on this maybe for almost 10 years. It's always funny because this feels like a very odd area. There used to be a very niche area. They probably had like 7 papers at NeurIPS in 2017 on this. But then it became really, really exciting, and there's now probably hundreds of papers every year about this. But it's always important to like remember that I mean this is an area that's pretty old, and it's for very funny reasons I'll actually mention. So basically, there has been foundational work even in the late 80s and early 90s on this, and we'll actually go over some of this. And these papers are Optimal Brain Damage by Jan LeCun and co-authors, and then Hasibi, Stork, and Wolf. They had this kind of paper in '93 on optimal brain surgeon that we're actually going to cover today in a bit of detail. And then people also came up with fairly simple heuristics, like taking a neural network's weights and sorting them by magnitudes and pruning the ones that are very small that seem to be very, like they seem to be close to state of the art even today. And then even Schmidt-Huber in a paper in 2002, he actually mentioned something that is kind of maybe like the bitter lesson. It's a bit hard to tell, but it's never a bad idea to put a citation to Schmidt-Huber in your slide. So I just I decided to do it. Anyway, let's move on. So after that, there was this period when people didn't care too much about deep learning or basically neural networks, and so there wasn't that much happening. And then interestingly, people kind of rediscovered a lot of the methods that had been introduced in the 80s. They kind of rediscovered them in the area in this range of 2015 to 2020. And then I would say right now we're kind of in a third age period of compression where it has become kind of a big business. So we have computational support for compressed data types on NVIDIA GPUs, on CPUs, on IPUs and TPUs and so on. And then there's better methods that can actually have quite a bit of impact. And then there's also a lot of challenges. There's kind of work on theoretical support and challenges regarding like bias or transferability in compressed models and so on. So I mean, and in some sense, this distinction between the second and third ages, this is more of a didactic separation. However, it's really important to know that like modern compression methods are really widely deployed. I believe pretty much every open or closed lab that is deploying models will use some kind of compression. And then these methods are applicable at scale. They provide major practical speedups. And as of earlier this year, they can tank the Korean stock market. So basically, this is, for those of you who are not following the Korean stock market, this is the TurboQuant incident. This is a bit small. So basically, there was this paper by Google earlier this year, which was a KV cache compression technique, which led to the stocks of Samsung going down by 50% in one day, or like some ridiculous thing like that. Fortunately, everyone's fine and the stock went back up, but it was quite shocking to see that something like this can actually happen. So, okay, so what is this compression problem about? So let's get a bit more technical. So the basic issue that we are trying to solve is we have an accurate deep neural network that someone spent $2 billion to train. And then we essentially want to find a compressed subnetwork or surrogate of this network, such as the loss, let's say the eval loss of C is the same, the compressed one is approximately the eval loss of N, okay? So for example, in network pruning, we essentially train the network on your left, and then we essentially want to obtain a sparsified version on the right, okay? And it's kind of, so this idea is really inspired by synaptic pruning, which actually occurs, I believe, at least twice in a generalized manner in the human brain, I think around 2-3 years and around 14 years old. So yeah, so how can we model this mathematically? So this is a rough outline of what these two optimal brain damage and optimal brain surgeon papers are kind of presenting. So essentially they say, okay, you have the trained weights, which I'm going to call W. You can think of them as this W star. These are well-optimized weights. And then you're going to apply a compression operation. So you want to obtain the compressed version of W. And this is basically W plus a perturbation of a very specific kind, right? So your perturbation has to have the property that it's going to prune out at least one weight, okay? So then, assuming that this perturbation is small, we can say that the loss at the compressed model is, by Taylor's approximation, the loss of the original model plus the gradient of the loss with respect to the original weights times the perturbation plus this second order term, which is delta transposed H delta. And then we're going to assume that the perturbation is small, so the third order terms will disappear. Okay, does this make sense? Any questions? Okay, this is totally standard. Now, it's very common to assume, I mean, this is something that can be baked into the method if you want, but basically it's very common to assume that the second term is negligible because the gradient of your original model is very small. That's why you trained it, in order to reduce the gradient down to 0. So basically, notice that we want to minimize the difference between these two terms. This is the loss of the compressed model. This is the loss of the original model. So we want to minimize the difference between these two. And this is equivalent to minimizing the difference, basically this third term. That's literally what happens if you take the gradient to be near 0 and move things around, okay? So essentially, we have reduced the problem of finding the optimal perturbation for compression to the problem of solving this quadratic form under a very specific perturbation, like structure of the perturbation, which is essentially that the perturbation has to sparsify some weight I. Okay, we want to remove at least one weight, which is equivalent to saying that the ith basis vector times the perturbation plus the weight itself is going to give us 0. Does that make sense? So we're just trying to optimize this simple quadratic form under a constraint. So does anyone know how we could do that? Like, are you familiar with? Yeah, exactly. Lagrange multipliers. You can just shout. It's fine. It's too complicated for. Yeah. So basically, you would apply Lagrange multipliers. I mean, we're not going to do it today because we don't have that much time. But basically, to prune or zero out the best weights WI, the optimal answer is essentially you want to choose the weight with minimal loss impact, which is basically the one. I mean, you can work it out to be the weight with the minimum WI square over 2 times inverse Hessian on inverse Hessian diagonal corresponding to that weight. And then the optimal perturbation with respect to this is going to be, it's going to have this form. Okay, so I mean, I'm going to try to give you some intuition for why it looks like this in a second on the next slide. But notice that we kind of need a couple of critical things to derive this. So in particular, we would need to compute to invert the Hessian and then to obtain the inverse Hessian, like inverse the diagonal entries of the inverse Hessian, okay, which some might sound complicated. And then also to check our work, we can actually say, okay, what happens if the Hessian is completely the identity? So which means that these weights are completely uncorrelated in our problem. Then can someone guess what the best way to remove would be? If this is the identity? The smallest way. So basically we have reproduced this magnitude pruning baseline that's very good. It was invented by Hajawara in 94, just by in a very fancy way in some sense. Okay, so it does seem, our derivation does seem to make sense. Okay, and then to kind of try to understand why this happens, we can look at this kind of 3 blue, 1 brown type of setup. So let's assume we have a quadratic form with non-trivial Hessian. Okay, this is the Hessian. And then, so you can just form the quadratic form this way. And let's assume we're here, and these are basically the level sets of my quadratic. And then, like, notice that, so well, I have W1 and W2. Now, let's imagine that I'm trying to decide which one I want to prune. Notice that the direct way to do it, if I just look at, like, if I don't look at the curvature information at all, then the best way to do it would just be to like 0 out 1, and then this would move me here on the loss surface, basically on the on the level sets. However, there is actually a much better way to do it, which would be here, but this required kind of changing the other weight as well, right? So basically taking into account the correlation, and this is exactly what this form does, right? So instead of just projecting directly, just picking as if they are uncorrelated, it actually takes the correlation into account. So if we're removing weight 2, it also updates weight 1 to take that into account, right? So it moves us to a strictly better level set. So instead of here, it moves us to here. Okay, does that make sense? All right, good. So good. So okay, so in some sense, to check our work or make sure that we are kind of all following, let's do this again, but we'll do it for a different type of compression, which is going to be quantization, which turns out to be much better in practice. So this is why I'm going to redo this. I'm going to not spend that much time on it the second time around. But to understand what quantization is, essentially, like, this is the original weight distribution of a neural network. This is, I think, a DNN that I trained on CFAR a long time ago. And then basically what you want to do is you want to bucketize the weights to a set of integer values. So essentially to uniformly spaced out values. So this is the same as histogramming your weights. Does that make sense? And notice that if here I need kind of very high precision to store my weights, because this delta between two weights can be very, very small. On this other end, the deltas are kind of fixed quanta, which is why this is called the linear quantized form of the weights, okay? So notice that if here I needed a lot of bits to store the value of a weight, here I only need like the integer index of the corresponding bin for the weight, okay? So now this is, I would say, probably the most popular model compression technique. And what happens usually is you're applying this post-training quantization, which we'll also do later today, which says essentially we have an already trained model, let's say in 16-bit. It looks very colorful. And then you essentially want to apply a fancy numerical technique that's going to allow you to map this colorful map to a less colorful map, which just needs less bits to represent the weights. Okay, does that make sense? Okay, so intuitively, this I think is pretty clear. The reason why we're doing this is very simple, and I apologize to those of you in the back who maybe can't see this. But basically, like neural networks, when they run their very large matmoles, like very large matrix multiplications, so we want to replace the precision at which this large matrix multiplications are happening, because the lower the precision, the higher the speed, and the lower the energy that you need to do the matrix multiplication. So for instance, you get 2x if you switch from BF16 to 8-bit multiplication. You get 4x if you switch to 4-bit. And then if by some miracle you were able to do your multiplies in 1-bit, which is unfortunately not possible, then you would be able to do your matmul 16 times faster, right? So basically you would literally get a 16 times faster model just for the price of optimizing it in 1-bit. Okay, so just to check that we're sort of at peace with the previous derivation, how does this apply to quantization? Well, it's literally the same thing, except that our perturbation has encodes a different constraint. So basically, we again we apply Taylor, the gradient is again 0. We need to minimize this quadratic form again. And notice that our perturbation has to be of the form that it maps weights to a lattice, which is kind of described by the whatever sort of quantization scheme we're using, right? So basically, if you want 4-bit matrix multiplies, then you want to make sure that your weights are going to be representable by 4-bit uniform quantization, okay? And now I'm not going to ask you to derive this online, but basically the loss, we are going to obtain that the loss impact is going to be, instead of wi squared over twice the inverse Hessian, is going to be wi minus q of wi. So basically that's the quantization loss square over the inverse Hessian. And then the optimal update is going to be exactly the same, but where we replace wi with wi minus q of wi. Okay, so that's pretty nice. And can anyone, I mean, I think this is a bit hard to tell, especially since this is on the bottom of the slide. But basically, again, we need the diagonal of the inverse Hessian. And then we actually will, if we have assumed that our weights are uncorrelated, basically the analog of magnitude pruning just says that you should always round the weight to its closest quantized point. So basically, we obtain again round to nearest quantization, which is by far the most practical, sort of the most popular quantization approach in practice, but it's also the least sort of performant. Okay, so I think we have derived a very nice mathematical formulation for quantization. So at least I find it very pleasing. Can someone tell me what the issue with this is? I mean, I wouldn't say, I mean, the thing is, usually you normalize before you quantize. So the fact that, I mean, if your weights are, I mean, sure, we might want to have a different type of grids that's not uniform. However, I mean, modern GPUs already have this. So basically they will support a floating point form, but more in the like fundamental sense. Like basically, if I asked you to implement this, what would be your first difficulty if I asked you to implement this algorithm? It's not.
So it introduces like high frequency noise into the vector of the.
We'll see that. Fortunately, this is not the case. I mean, basically, you can. I mean, it's a fairly complex numerical method, but you can dampen, like you can apply. But it's a good point, but it can be overcome.
Also, you have to like move back and forth from integer space to float space.
I think you guys are overthinking this. I mean, the problem is very basic, right? Okay. I mean, okay, like I just like 5 slides ago, I told you about this behemoth model that has like 2 trillion parameters. And then I'm asking you to compute the Hessian of this and invert the Hessian of this. I mean, basically, you probably would need the remaining history of the universe to essentially invert the Hessian of like a trillion parameter model. So that was basically the question, the point. So the issue here is that you can't compute this. You can't even store it. So just to get kind of an intuition, like the Hessian of ResNet 50, if you were to store it, it would be 25 petabytes of data. So that's all of the data I have at my institute. So basically, we would need to wipe out everyone's data just to store it. And then we probably would need to wait for 500 years to invert it. So it's a more fundamental problem, which is you can't compute it, you can't store it. Yeah, works. I'll repeat your question.
What about numerical tricks like inverse Hessian vector products? Does that help?
This is exactly what we're going to do. Yeah, that's good. That's a good point. Yeah. Okay, so I'll just give you kind of a rough approximation because just so you kind of see what people have been using. So for instance, the original paper by LeCun essentially assumed that the Hessian is diagonal. And then you don't have this issue because you can just invert each entry on the diagonal. Unfortunately, the hashing for deep nets is not diagonal. So you actually get pretty bad answers if you do this. There are tricks like the Fisher approximation, which essentially says the Hessian is approximately the empirical Fisher. This is not Razvan's favorite approximation, as you could see for his reaction, like, okay, his immediate reaction was like, I don't think I like this. So yeah, basically, what this is it's essentially the average over outer products of gradients taken at the optimum point. So it's, I mean, some people like it. It's more like a religious thing, but you can use it, but it's not that useful. And the key issue is if you have such a massive model, it's very expensive to take gradients, and then forming this outer product would be also like prohibitively expensive. Okay, and then there are other approximations like KFAC and so on, which are very interesting. I invite you to have a look at them, but I'm not going to cover in this talk. So the tension here is between the fact that we kind of have this very tempting mathematical framework on the one hand, and the kind of practical impossibility of applying it to modern methods, right? So that's kind of the thing that we are trying to resolve for the remainder of this lecture. So essentially, like my lab's approach, as I said, like we've been working on this for at least 6 years, has been to essentially come up with what he was suggesting, which is basically a set of numerical tricks, which is a toolbox of linear time, linear space, numerical algorithms in like linear, I mean in the model dimension for estimating second order information about deep net. So what I mean by this is that we can't form this large matrix, but we can query individual elements and we can sort of do products, like basically vector products against it. So that turns out to be useful. And then turns out like you can apply different types of tricks to different parts of the network. So essentially, if you want a blockwise approximation, essentially for like an attention block, then you will do a specific type of approximation. And then if you want to do layer-wise, then there are other, additional tricks. And then if you really want to get global information, there's like additional types of tricks. So it's kind of a very nice space algorithmically from this point of view. And yeah, the other thing is like if you want accurate approximations, it seems like really you need different levels of granularity for different types of models. So what I mean by linear here is literally linear in the model dimension. So which is pretty much what you deal with when you do like, let's say, backprop over a model. So that should be the order of the cost. Okay. So I think I think I gave you kind of a general introduction into the area. So then I'll talk a bit about one specific algorithm that became fairly popular, which is called GPTQ. So basically, as I was saying, like for million parameter models, so like if we were still dealing with ResNet 50, which has 25 million parameters, then you could actually solve the problem by essentially retraining the model in some sense. So basically, you take your weights, and then you're going to take backward passes. You apply straight through estimation, and then you usually get something reasonable. However, these billion parameter models, such as GPT-3, basically OPT 175B, which are now fairly common, these are 1,000 times larger. So basically, when we started this research, we couldn't even do a single backward pass over such a model. Like we could barely store it for inference. Okay, so instead we essentially needed to find a new way of doing this in basically in one shot. So basically we wanted to do it at the level of doing forward passes over this. And when we started, I don't think there were no non-trivial methods. And then you can of course do round to nearest quantization, but this really tanks the model accuracy. So this didn't perform very well. So the general approach is a very standard approach in computer science, which we call divide and conquer. So essentially what we are doing is we take a trained network, let's call this network W, and we are going to slice it into layers. So these layers are either MLPs or attention projections. In some sense, we don't care. We're just going to slice it into individual layers with the property that each layer has like an input, which I'm going to call Xi, and an output that I'm going to call Yi. Okay. So, okay, so for each, and then we take some data, let's say some sequences from Wikitext, and then we run it through the network, only doing forward passes, okay? So then this gives us for each layer wi an input xi and an output yi. Okay, and imagine that we essentially set our sights on the following very simple regression problem. So essentially, I want to find the solution to the problem of finding a quantized set of weights or sparse set of weights. I'm going to call it wi hat, which best approximates in L2 norm or Frobenius norm the output of the original layer. So basically, I want to find like the wi hat, the layer compressed weights, which have the same response over the input xi as the original one. Okay, good. So it's not that complicated. And notice that this thing, like the wi xi, is literally yi, which is something that we can store. Okay. So and then the key property is that this should satisfy a given sparsity or compression constraint. So basically, the wi hat has to be sparse or quantized, otherwise we haven't really solved anything. Okay. Notice that from the theoretical point of view, we have taken a very massive NP hard problem, and we have turned it into a smaller NP hard problem. So like sparse regression itself, like finding the optimal solution to this, is NP hard. So basically, I mean, you can't guarantee that you have found the optimal solution. Okay, we can only hope that we can find individual layer-wise solutions with low enough error that we can actually put together the, like we essentially break the problem apart, we solve each subproblem, we put it back together, and then we hope that that model still continues to work. Okay, and that's not the guarantee. Okay, and we'll see in a couple of slides time that this can be pretty bad. Okay, so now imagine that the only thing I know, or the only math I understand, is basically this optimal brain surgeon. So why not? I might just try to do it and see what the problem is. Okay, so let's consider this for quantization, which is the last thing that we've seen. So remember that the optimal quantization for such a layer is going to be like we rank the weights by loss impact, which is basically the quantized value minus the original value over twice the Hessian inverse. And the optimal update is, which basically warps the other weights to kind of compensate for the loss, is basically this thing over here. Okay, so notice this gives me the optimal order and the optimal update of the remaining weights. Okay, so what is the issue if I just try to apply this? I mean, it's the same as before, right? So maybe one thing to notice is that, I mean, like trying to find the optimal order in which to quantize a billion weights probably doesn't matter too much. So basically, the order in which you, like, whether you do, I don't know, one weight ahead of another, then it doesn't matter too much. But even if we just wanted to apply this type of update, we have exactly the same issue as before, right? Like it just the same issue, but I don't know, 1,000 times larger. In this case, actually 1,000,000 times larger because the complexity is quadratic. Okay. However, there is like a trick here, and if you have been extremely attentive, you might have caught it. So there is like a nice trick, which has to do with the loss that we are optimizing. Yeah, it's a quadratic, and great. And why is it nice that we have a quadratic? I didn't even see who said quadratic, so I'm sorry. I'm just looking in that. Oh yeah, okay. You may be cheating here, but let's go on. So maybe you've seen a version of this talk before, but basically, what's so useful about the quadratic when it comes to these second order approximations? It's constant. Great. So let me explain what. Very good. Excellent. I will tell Eldar that you answered this question. So, so basically, recall that we're minimizing a layer-wise L2 loss, which is basically original output minus X times quantized, okay? And the Hessian of this is Xi transpose, or Xi transpose Xi, depending on which layout you like, okay? This is constant with respect to the weights. So basically, whenever I'm doing my forward passes to collect the Xis, I can actually compute this xi transpose and kind of keep it on the side. Okay, this doesn't, if I update my weights or if I quantize the weights, the Hessian doesn't change. It's the same weights. It's because it doesn't have any W term in it. It's only xi's. Okay, so the Hessian is constant. And then you can be pre-computed at the beginning of the process. So then what you can do is you essentially you have your massive weight matrix here for layer I, and then you quantize it using some kind of order, whatever. And then you go over columns, basically one column at a time. You quantize the elements in the column. And then what it can do is like you can still correct the sort of error impact of quantizing this column by adjusting all of the other weights. So you're essentially solving kind of an incremental regression problem in order to minimize your loss impact end to end. Okay, so I know this is a bit complicated, so I have another 3 blue 1 brown illustration to show it. So basically, this is the Hessian, which hopefully you believe me is constant. Basically, if you double differentiate a quadratic second order sort of polynomial, hopefully we all agree here you get a constant. Okay, so this is essentially my Hessian. So pre-computed and constant. Then this is my original weight matrix, which can be very, very large. So then what do? I go column by column. And then I quantize the current column. Let's say, like notice they're all 1, 0, or -1. And then whenever I quantize, notice that each one of these will have an induced error. Oh, sorry, I mistakenly restarted this. So we quantize. And we register our output errors with respect to like the output errors that kind of we obtain by quantizing each one of these elements on each column. And then we apply the magical delta formula from Lecun in order to update all of the remaining weights on all of the remaining columns to compensate for the output error. And then we do it again. Errors, updates, and again, and again, and again. So we basically go step by step this way. All right. And notice that the key component here, this is what basically lights up, is these are the correlations between this column and all of the remaining columns. They're encoded in the corresponding Hessian sort of sub entries. Okay. All right. So that's it. Any questions about this? Yes.
Why are we still looking at the second order? Why do we think that the gradient is 0 in this case? This is not the loss function anymore, right?
Because that's a great question. So in this case, so you remember, so we had this Fisher, we had the Taylor approximation, right? And essentially we said that the Taylor approximation is like the loss of the quantized point. I can actually go back. The loss of the quantized point is the loss, the loss of the quantized point is approximately the loss of the original point plus this thing plus this, right? But notice that in this case, my function is actually a quadratic. So what this means is that this term is by definition 0. Like basically my function is only, like the difference here is literally this, because what happens, it's literally the same to saying, I mean, okay. So this is the problem that I'm solving. And what you're saying is the gradient 0? Well, the gradient is 0 for the following reason. If I set wi hat here to wi, my loss is 0. So basically my function is, basically my approximation is exact for a quadratic. So I don't need to take into account the gradient term. Does that make sense?
So our goal is to be close to WI. Like we can't choose WI head to be WI. Why doesn't, I don't understand why is the number here of smaller magnitude than the other.
I'm not sure I understand which number.
So this is not actually 0, no? Because
it's not.
I think it's the expansion is around W.
The expansion is around W, not around WI.
So like at the point where you make the expansion, the loss is 0. So like that gradient is going to be 0.
Yeah, you got it. Yes. Let's take this offline because I really want to show you some actual results. So this is the algorithm. I'm around afterwards, so feel free to ask me more stuff about it. So it's good to maybe take a step back, take a breath, and let's look at some nice pictures for a couple of minutes, so we're not so stressed about equations. So basically, let's see if this actually works, and if it does work, how well does it work? So these are the original results, and I'll show you like some results from a much larger scale study that we did last year. So essentially, the standard way to measure loss is perplexity for these models. These experiments were done 3 years ago already, but they actually hold up pretty well. So these are OPT model family models. So these are the same like reconstitution of GPT-3. So this is, if you recall, if you've ever worked with this, maybe this was before your time, but basically you had models at sizes, I think 1 billion, 7 billion, 13 billion, 70 billion, 175 billion. So basically these are the model sizes. This is basically the kind of bitter lesson type of thing. So basically this is, you have number of parameters, and then this is your loss or your perplexity over as you increase the number of parameters. So the dotted black is the actual, like the uncompressed model. And then if you apply round to nearest quantization, which is basically you take each weight and you round it directly to the like closest quantization point, then you essentially get this weird like jagged format. So basically your perplexity increases is very high, and then it's also not very predictable. So you have some models that get completely destroyed, okay? And this is what happens if you apply this GPTQ method, and this is all 4-bit quantization of the weights. So notice that there is a significant gap for the small models. These are kind of 1 billion parameter models. But then here, the loss in terms of perplexity is really, really tiny. So essentially, this is almost lossless for OPT175B. I mean, this wasn't such a great model to begin with, so I don't think the battle is won. But you can definitely see that the method works better than any alternative. Okay, and then the other thing is like we also ran it on Bloom models, which were Hugging Faces reproduction. These were even worse, so I won't spend too much time on this. Maybe one historical note. So when we were done with this, we were quite happy. And one thing I invite you to do in case, like after you're done with your NeurIPS rebuttals and so on, is just Google the paper and go to the open review page and try to see how much pain we had in dealing with the reviewers trying to convince them this actually makes sense and is useful. So this is just, I mean, this is not to sort of push my own paper, but really it's just a way for you guys to see that sometimes just people don't get really what you're trying to do. And that's fine. So just to like go through the revisions, do what they're telling you to do, make the paper better, and it's going to be fine. So maybe that's basically my advice to you based on this paper. Just, I mean, reviewer 3 was really bad. Anyway, so let's move on. So okay, so basically the idea is that you can quantize these models down to 4 bits, and it works really well. And the interesting thing is that this did lead us to some real improvements in terms of the number of GPUs, or like the compute or cost that you needed to serve these models back in the day. So essentially, the OPT175B model, you basically needed a full server with 8 GPUs just to store the weights. But if you compress it to 3 bits per weight, which has like a 0.34 loss in perplexity, which is, I mean, it's not negligible, but it's not very high either. then basically you can keep the entire model in a single GPU. So this is very similar to what methods such as Llama CPP do these days and so on. So this allows you to keep the weights in GPU memory very efficiently. And then whenever you actually need to do the matrix vector product that's required to generate the next token, you essentially copy the chunk of the matrix into registers, you upscale this, you do the multiplication, you obtain the next token value, and then you go on, like you drop the matrix, you load the next compressed one, and so on and so forth. So basically, this dequantization technique, I think, was quite a nice trick. So then what this allows you to get is essentially a reduction in the number of GPUs needed to serve these models. And this also gives you quite a massive speed up because the generation process in large LLMs is memory bound. So you're basically paying mostly for the cost of copying the weights into the GPU memory or your CPU memory. And then if you reduce this cost by 4x, you get a speed up that's around 3.5x. Okay, hopefully you'll see this also in practice this afternoon. Okay, and this became quite popular, and I mean, you can find it online if you want to play with it. So now, taking a step back, I mean, these results were basically 3 years old, but I think it's a good way of explaining what this compression stuff is about. And now I think today the space has really expanded quite a lot in the sense that you have a lot more techniques like quantization, pruning, this for a talk a couple of months ago. So one thing is basically so we actually were putting models in GPTQ format on Hugging Face up to some point. At some point we kind of gave up because no student was interested. But I just checked the number of downloads for these models, and this is around 55 million or something like that. And then for other methods such as Llama CPP, the number of downloads is really alarming. So it's kind of a nice area if you like people adopting your work and deploying it and so on. Okay, so maybe the last question I want to cover is where is this going? So essentially, what can we do? What can we do in the future for quantization? And I want to cover this from both the practical perspective and just give you a bit of theory. And as all good research, I think this direction was inspired by a tweet by this guy on the internet. And he was very upset because he tried a quantized model and it didn't work. And then he said, give me the full precision model or give me death. Otherwise, I really don't want to see a quantized model again. It turns out this person had misconfigured their harness. So this was actually not, we talked to him afterwards. But it did inspire some interesting research. So basically, this was a paper we presented last year at ACL, and it's a collaboration with Red Hat. So basically, we looked at pretty much all of the popular techniques about maybe a year ago, including GPTQ, but also some other ones. And then we looked at methods that can be run efficiently on GPUs, in particular, 4-bit weights, 16-bit activations. So pretty much what I described before, but also mapping both weights and activations to 8-bit. Okay. And then we ran academic benchmarks. Maybe you've seen like OpenLM leaderboard, like MMLU, these types of things, but also some more expensive generative benchmarks, such as the ones that, for instance, OpenAI used to run when releasing models. And then we ran standard models like Llama, Qwen, Gemma, and so on, but also large MOEs like DeepSeek, DeepSeek R1, and so on. These were very popular back then, also Kimi K2. So this was quite a big study. I think when we started, we kind of thought, okay, this would maybe take a month and maybe yield some interesting data. But all in all, I think this took maybe more than 6 months and more than 1 million individual task model evaluations. So here I really want to emphasize the Chuck Norris of quantization, which is Eldar Kurtic, who actually was able to run all of this stuff and still maintain his mental sanity. I mean, like 1 million experiments is very hard to kind of keep track of, to be honest. Okay, so basically, I'm just going to give you the findings in one slide. So the current state of the art is that when done properly, unlike the guy on the internet, 8-bit quantization is essentially lossless. So we basically, I mean, I'm not going to go over what these graphs mean, but hopefully we can all agree that they basically, the blue one is the baseline, and all of the methods are at the same level as the baseline. That's where what we're going to keep it at. And then, like, if you try to do a 4-bit quantization, so more aggressive quantization, pretty much all of the compression approaches we tried were about 1% of the baseline on easy benchmarks, but then you can drop more on reasoning benchmarks and so on. So that's, I think, a good state of the art. And then if you try to quantize very large models, such as like 70 billion plus, then this turns out to be quite easy. So basically you can pretty much maintain accuracy at 4-bit, which is why also I think, for instance, K3 is released with 4-bit weights already. So this is basically the empirical state of the art. But then the thing I want to end on is basically whether there is much, like, is there a way of actually doing this losslessly with guarantees? Or is there this kind of 1% that we have observed empirically sort of inherent? And I mean, notice that, like, at the fundamental level, there should be something lost, because quantization is a bit like adding noise to your weights. So basically, you'll not be able to preserve your output entirely. So then it's a question of how much does, like, how much is what is really the output impact of your quantization noise, which again is very similar to this kind of intuition that the Taylor approximation gives us, right? So we're adding some delta, and then we want to know what the output loss is. So this is work that was led by Andrei Panferov, who's going to give you the lecture in the afternoon, as well as Vladimir Malinovsky. And the question is really, can we predict the accuracy impact of quantization? So the theoretical claim, you can actually find like a theorem on this. It's called the linearity theorem, is that under many assumptions, which happen to be convenient for approximating, the impact of quantization over like a smooth function such as perplexity is approximately linear in the relative layer-wise L2 error. So what do I mean by this? So if you want to see what the difference in perplexity is between the quantized model, this is basically the expected perplexity of W hat, versus the original model, well, this difference is actually a weighted sum of error, of layer-wise error. So basically you have like alpha L, which is essentially like a sensitivity coefficient for layer L, times TL, which is the L2 error at layer L. So basically this is the output, these kind of W errors you were asking about. This is basically this is the gap. So what you can think about is like each layer has its own kind of sensitivity factor, and then these act linearly on the increase in perplexity at the end of the network, which if you kind of backtrack and try to understand what this means about the Hessian, it tells you that the Hessian is approximately block diagonal over the entire network, okay? And this only holds for a specific set of methods, in particular without weight updates. So it doesn't apply directly to GBTQ, even though you can extend it in that case. So why does this matter? Well, this is kind of interesting for a couple of reasons. So one thing is that we can actually predict what the quantization impact for a model is going to be, as long as the error is not too high. So this graph essentially shows you what's happening, because we're taking a model. I think this is a Quen or Llama model, and then we essentially estimate the perplexity increase. This is this sort of dotted line here. And then we actually quantize the model to the corresponding bit width, and then we put the points at each step, okay? And notice that up to around 3 bits per parameter, our predictions are exactly on the line. And then once we are going below 3 bits per parameter, our predictions are way more optimistic than the actual impact. So what's happening here is that, I mean, there are several possible explanations for what happens at lower bit widths, but what happens is that one thing that happens is that certain layers get really damaged, and therefore you don't get enough signal past that layer. So basically you're not now starting to have correlations between pairs of layers because one earlier one gets damaged too much. However, we're very happy with the fact that we can essentially interpolate or predict very well in this kind of high precision, like high accuracy regime. And then this also tells you kind of what the lower bound is, right? Because I mean, if you have 3 bits per parameter, there's only so much noise that you can minimize, right? Basically, there's going to be like there's some kind of information theoretic value of the minimal amount of noise that you can express with 3-bit weights. So then essentially it also tells us what's kind of the minimal amount of quantization error that we can resolve, right? So, and then, I mean, this also inspired an approach that I'm maybe not going to go into. So basically, what I want to say is that we're really at the stage where we can kind of understand what the limits are, but also sort of know that we're very, very close to the limits. In particular, there are methods that are very complex. I won't touch them in this talk, like QTIP and NestQuant, that are really at the limit. So essentially, like if you're willing to pay the implementation cost, you can get really, really close to the information theoretic limit for these methods. Okay, so maybe I'll wrap up here. I just wanna maybe show one last slide. Just give me a second. Yeah. So I just wanted to, I mean, so I started from the bitter lesson. So I just want to come back to it in the end. So essentially, what you've seen today is a bit like the bitter lesson squared, because basically we're designing computationally efficient methods such as GPTQ to make LLMs more computationally efficient. So basically, we're trying to build some kind of limited recursion here, or at least a kind of a first step update here. And then I also try to convince you that there is some interesting math in the area. So basically, you can apply your favorite, I don't know, like second order approximation. And this is like a very good area to look at if you're really into algorithms and efficiency, also like GPU implementations and so on. So the challenge is really to come up with fast but also well justified approximation. It's relatively easy to try things out. So then the frontier that I didn't touch today is basically what if we try to train models in a quantized, like in a directly quantized. And I think this is really one thing where we don't fully understand. And this requires you to rethink, for instance, backpropagation, because it has to happen over a discrete set. And then there's really big open questions in terms of like what hardware do we want to run on, what kind of optimizers we want to run with, and what kind of like what are the limits of compute. So thank you, and I'll stop here.
Okay, so we already have questions.
Yeah. Hi, thank you very much for the very brilliant lecture. So regarding your visual diagram for the GPTQ methods, I would like to ask, is it possible to make more iterations? For example, on each column, you first give kind of very large update, some like 0, maybe 1's points, but maybe, for example, if you first give an update to some other lattice in the subspace, which should be more fine-grained, and then repeat it more times, maybe it will work better. What do you think?
Yeah, so I think that's actually not a bad idea at all. I think that there is this algorithm that was actually proposed very recently called EEML that actually does something similar to what you're suggesting. So basically, it first quantizes to an easier lattice, and then basically, so it does this kind of progressive. So it's a bit like you run GPTQ. I mean, it doesn't do that exactly, but it would be a bit like you run GPTQ at 8-bit, and then you run it at 4-bit, and then you run it at 3-bit, and so on. So this kind of iterative. So definitely possible and not a bad idea.
Yeah, it was amazing lecture. Yeah, and but I also thought about regarding GPTQ method, why we have speed up in token generation. I recognize that we can compress the model to to share more questions in parallel, but why we have speed up? After quantization in 4-bit or 3-bit, we have requantized the weights to 16-bit or 8-bit. Yeah, it depends on our computation card. And yeah, why we have speed up?
Yeah, so basically imagine that imagine that I'm here and you're there and you have the weights, and basically we have a pipe between us and I have to suck the weights over on my side, okay? Basically, and the weights are like 10 liters, okay? And then essentially I have to, every time I want to do the computation over the weights, I have to bring the weights over on my side, and the pipe is this size, okay? So it's going to take a while, right, to bring 10 liters over on this side, okay? So notice, like, in order to generate the next token, I need to see all of the weights, right? Okay, so now what does GPTQ do? Essentially, the weights are at, 16 liters initially. Now it reduces the weights to 4 liters, okay? So basically, the point is, it's just going to take less time. It's going to take roughly 1/4 of the time because it's lower volume of weights that have to get on my side. Does that make any sense? I mean, I think maybe the question you're asking is a bit deeper, because you're saying I only quantize the weights, but I don't quantize the activation. So basically, I still have to perform the computation in 16-bit when I do it. But the point is, so here it has to do more with architecture of the GPU. So basically, like the GPU is very powerful for matrix multiplication. So what happens is whenever we run the model, we essentially need to bring in the weight matrix for, let's say, the first projection. And then I need to multiply that huge matrix with a vector, which is the embedding vector at that stage of the network, right? And then I throw away I only keep the resulting vector, basically the updated embedding vector. And then I throw away the matrix, and I need to bring in the next matrix from your side, right? And then I take that and I multiply it again. So the point is, the main cost for basically for generation is actually a matrix vector product, which is memory bound. It's not compute bound. It's like for the GPU, the time to do the multiplication is negligible. The real cost is bringing the weights from you to me. Does that make sense? So that's why we get speed up, okay? No, I can follow up and explain this a bit better.
Yeah, okay, thanks again for the lecture. And when you think of current models as a compression engines, you're trying to model 30 trillion tokens into 2 trillion weights. The fact that you can get half, you can reduce this model size by half with like almost zero loss in inaccuracy, it suggests that either these models are not particularly efficiently trained to begin with, or that we pay for it in some other way that the benchmarks don't measure. So my question is, do you think that the lunch is extremely cheap, or do we pay for it in some other way?
Okay, I mean, I think that's a very good question, and that's a bit of a trick question in some sense, because I don't know the right answer. I mean, there might always be something that is lost. So I think it's very hard when you have a very powerful model to make sure that you're not dropping anything, because you cannot run it on overall possible inputs. I mean, one possible reason for why this works and is applied quite broadly is that a lot of the overparameterization you may need during training. So basically, you might need the extra parameters, extra cost, extra layers. You might need them at training time in order to obtain a stable and good model. And then once you have obtained that artifact, then it's fine to start dropping stuff. So my point is not that this is the bits are useless. It's just that the bits are probably useful for something that you may no longer need at inference time, so it's fine to drop it. So yeah, I mean, one possible explanation is you might need the extra precision in the weights to essentially make sure that your back propagation is stable and so on. Okay, so I think so. Generally, I don't know, but it does seem like you can compress to 8-bit without really any issues.
I have one question.
Yeah.
Thank you for the great presentation. So what I wanted to ask is, do you always use uniform quantization levels, or is there some smarter way to do this?
Yeah, so basically, the short answer is no, we don't always use uniform quantization. So in particular, like on NVIDIA GPUs from the Blackwell line, you don't even have uniform quantization anymore. So basically, you have this FP4 quantization that is non-uniform. You can also do fancier quantization where you learn the grid. You basically adapt your grid before you do the quantization, and you can even repeat this. You can re-quantize, re-adapt the grid, and so on. So all of this is possible. So it's not tied to a uniform grid. Yeah, I only presented uniform stuff just because it's just easier to explain.
Thank you.
Yeah.
I guess one last question.
Thank you. And one question about dropping of performance on reasoning tasks. So, for example, one might expect that language models have the ability of compensating kind of errors. And if you quantize the model in maybe in some way, it might be the case that during reasoning, these errors not accumulate, but compensate. And in results, you might not see the drop on the reasoning benchmarks. So the question is, how do you think, is it even possible to do quantization which does not drop on reasoning benchmarks?
So this is an interesting. So I think this is an interesting question, and this is also something that's being researched very actively these days. So, for instance, one phenomenon that has been noticed by multiple labs in the past couple of months is that quantized reasoning models exhibit token inflation. So basically what happens is that they will generate more reasoning tokens before coming up with an answer than a model that hasn't been quantized. So you get to a really weird situation where there is no drop, for instance. Like in these experiments, we were actually doing kind of limited reasoning. So basically we said, okay, you only have this many tokens to reason, and then you have to output the answer. But if you don't control for this and you just let the model go, until it wants to output, then it will generate more tokens for the thinking trace and then decide. And then you get to a funny situation where, of course, it looks great because you didn't drop, but then end-to-end, the quantized model is actually slower than the original one because it has to generate more tokens, but it generates more tokens than the savings you had from quantization in the very beginning. So basically, you have another axis, so you need to like check what's happening there. And there was even another paper. I haven't read it very carefully, so I'll just explain it, or just describe it very quickly and imprecisely. So I think what they were saying is that the models, even if you ask them, if you extend, but just by a very little bit, the thinking trace, they will be able to give you the right answer, even though the right answer is not in the thinking trace. So basically, or like so in some sense, if you force them, they will actually give you the right answer, even though it's basically the thinking trace is incomplete. So in some sense, the model knows the answer, but it doesn't know that it knows the answer. I mean, it's something that's really, so it gets really weird. The one thing that is true is that like quantized models tend to have more soft output distribution. So essentially what that means is that they will use more filler words than are reasonable. So basically that causes this token inflation. Yeah. We can discuss this offline.
So Dan is going to be around for today. So when you see him, you can go and ask him questions. We're going to have lunch now, and after that at 2:30, please be back here so we can do our mentorship sessions and so forth. And let's thank the speaker again.
Just quick announcement, please vote in the channel for the shuttle you will use on Sunday. So you still have like 10 minutes to vote. Thanks.